On the other side, we had CCD. CMOS generally consumed less power, which meant less thermal noise. It also meant that our designs could be made more simple, as we wouldn't have to change our design for that. It also came in at a lower price, and so we ended up going for CMOS. Another thing we looked at was rolling shutter versus global shutter, and that one was quite obvious. We went for a global shutter as it captured every pixel at once and decreased the amount of distortion that comes with rolling shutter. That left us with 4 commercially available image sensors, as you see up here. Originally, we went for the onsemi MT9V, but due to some supply chain problems, we ended up changing that over to the onsemi Python 480, which is still really good. It has one of the lower pixel sizes, and also it has the highest frame rate. Unfortunately, it does consume the most amount of power, but it was still beneath our preset max of about 300 milliwatts for our image sensor. And then we had to develop a way of processing the image that came from the image sensor. We were mainly looking at 2 different microprocessors. On one hand, we had the Arduino Pretenta H7, and on the other, we had the STM32. Both great options. The Pretenta H7 offered us with a module that already worked off the shelf, but it consumed slightly more power, which wasn't a problem, but it also came in at a higher price. Now, looking at the STM32, it was cheaper, it was smaller, so it would be able to fit in our 50 by 50 size. It also had the ability to directly interface with the camera through its dedicated pins for DCMI, digital camera interface, which simplified our design and also allowed the images to be taken and stored at the same time we could do our processing. So we ended up going for the STM32. And the way that we were processing those images, you can see on this flow chart. First, we start with the image being taken and being filtered. Then we calculate the center of the stars. From the center of the stars, we calculate a vector to those, then match it to an onboard catalog, which is then we do some math and determine the exact quaternion necessary for the system. So going more in depth, we start with the basic image like the one on the left, and then we filter it out so that we take the 3 brightest stars on the image. So we're only left with the picture on the right. Next we use connected component labeling to weigh each pixel in the star and determine the precise geometric center of the star. From there, we're able to map the stars onto a 2D plane at the end of the lens, and then using that alongside the known focal length of our lens, we're able to assume a pinhole camera model and determine the exact vector to the star. Then we're able to match that to an onboard catalog that we have stored. We're using the Yale Bright Star catalog with over 9,000 bright stars on it. Then we solve Waba's problem utilizing the Quest algorithm, and we determine the quaternion necessary. Then, if you remember from earlier, we're able to send that down to the ground or to the peripheral, where we can input it into our software and be able to see where our satellite is pointing. Our system comes in at about 1.4-ish watts, which is under our preset 1.5 watt max. That's determined by our standard bus. It can only support 1.5 per peripheral, so that works perfectly. And as you can see, most of that power is coming from the microcontroller, which makes sense, as it's doing a lot of processing. Next, we have the cost. This is our biggest point. Our current prototype is coming in at about $1,400. Now, that's already below our $5,000 limit, but this is a prototype, and the prices are likely to go up. But even then, our $5,000 limit is already 80 to 90% cheaper than a standard star tracker. Now, It's important to realize that we're not competing with those high-end star trackers. We're aiming for a place somewhere between the sun sensor and the earth sensor. We're able to achieve higher accuracy, except we do consume more power, 1.5 watts, and it is generally a larger package as well. But in the end, we were able to make our product affordable as well and give it to universities as needed. And are there any questions? Yes, sir. Yes, our yes, sir. So the question was, how fast could we process our images and be able to develop our quaternions, correct? All right. Well, it's a while back. All right. So our image sensor is limited to a 480 megahertz, which is quite fast. And since we're using the DCMI pins on the STM32, we're able to process those images and store them for later processing, which does allow us to achieve higher, more calculations faster. Currently, we're looking for an update rate somewhere around 5 times per second, potentially faster, but this is, we're still in the prototyping, and if you get back to me after this, I can give you a better answer, if that's okay. Yeah.
Question, are you pulling the star catalog into your STM32 microcontroller, or are you kind of going out in the memory and coming back? How does that lookup work with the star catalog?
All right. So we have the star catalog saved on a separate memory on our board. His question was, how are we storing the star catalog? Is that correct?
Well, and how do you interact with it? Do you bring it in to the STM32? Do you have enough memory there, or you kind of have to work up?
So right now we have it stored on our onboard memory, and we're going back and forth. Thank you for your question, sir.
Yeah, thank you.
Any further questions? Yes, in the back.
Do you have plans with this prototype of testing it in some sort of like hardware-in-the-loop environment or night sky environment or anything to get actual results and add to solutions?
So his question was, do we have plans on testing our star tracker? Correct?
Yeah.
All right. Yeah, we do have plans to test it later. I'm working mainly on the electrical side of things, so I'm not too involved in that side. I can get back to you after this for that. But we do have our software that we're putting our data into and able to test it to a certain degree. All right, and one last question.
Are you planning to commercialize it? And you mentioned the price. Like, how would other people be able to get it if they wanted?
So, like our standard bus, we hope to be able to give it to other people, and yes, sorry. All right, but I'm running out of time, and if you have any further questions, I'll be here all week. Thank you for your time.
Amazing. Okay, hooray. Please join me in welcoming our next speaker, Steve Stem from Blue Canyon Technologies, who will be discussing with you providing cost-effective, high-performance mission opportunities with industry-leading avionics.
Should be out here.
Alrighty. Good morning. Hear me okay? My name's Steve Stem. As they said, I'm the technical director of our CubeSat products at Blue Canyon Technologies. I've been at Blue Canyon for 9.5 years. Watched it grow, but kind of the core and what I'm real enthusiast behind is our GNC performance and supporting the CubeSat form factor. I love the stuff that you're doing. Midshipman Diaz there talked about some of the really cool things happening, pushing the envelope. Today I'm going to talk to you about kind of a slight pivot in some of the product offerings that we're making to support a lot of these university and also kind of small DoD NASA missions to make perhaps things a little more accessible for you, a little bit better learning opportunities for some students. Quick little thing about Blue Canyon. Blue Canyon started in 2008. Our first CubeSat, which was Raven, launched in 2016. Since then, we've always had a CubeSat in orbit up until now, as we continue to fly many more. We just flew 2 more 16Us a week ago. We're really known for our precision GNC performance. We kind of came in from a bunch of people, including myself, from industry, classic aerospace industry, to kind of push the envelope in terms of what our pointing performance could be on a small spacecraft form factor. We offer both subsystems all the way up through CubeSats, our minisat product line, up to what we call our Saturn 400, which is a 400 kilogram minisat. All these going together in our Colorado facilities, Boulder and Lafayette. We also offer mission operations for a lot of folks. They don't want to deal with it. We'll go ahead, we'll take your tasking, we'll deliver your science to you. You don't have to worry about anything else. I think we're currently flying more than 20 spacecraft in our Mission Ops Center. A lot of it is lights out mission ops, along with autonomous mission recovery in case there's an anomaly. So now let's get to why I'm here. I think we all know a lot of opportunity, grant budgets are not increasing. We're seeing the pain on our side. We're not the cheapest provider of components at BCT. But we know all of you out there proposing things are pushing the envelope in terms of what the science is. You need better performing hardware. You also want to offer good development opportunities for your students. Cal Poly SLO here is a great example. Dr. Lightsey's lab at Georgia Tech is another example. You are growing our engineers in the future. And you don't want someone who's just going to do the whole shebang for you, generally. You want to give an opportunity for your students. But you also don't want to waste your time on things that people have solved. GNC, computers, you want to be able to focus on some pretty cool payloads. So this product, I think, is going to help you. And as we said, we know that your budgets are constrained. A lot of NASA opportunity budgets haven't increased in their cap in probably 6, 8, 10 years. We're feeling the pinch. We know you're feeling the pinch. So we're hoping that this offering will help you a little bit and bring us some more business. Previously, in the history of Blue Canyon, we've offered one avionics package without a bus. That was for the LunaMap mission with Arizona State on Artemis 1. In general, we wanted to have the whole shebang, the structure, power, all the avionics. You deliver us a payload, or we give you the bus. What we've decided to do, because we think that's going to help you all out, is offer our avionics as a standalone package. So this avionics has our full GNC system, single star tracker, 50 Newton-meter second wheels, or millimeter second wheels, GPS and antenna, electromagnets, IMU. It also has all of our core heritage avionics algorithms. Those algorithms support missions everywhere from LEO to deep space, and they've been demonstrated in all those regimes. Addition to that, adding our power system, which includes a standard 6-cell lithium-ion battery, all compliant with SpaceX launch requirements, safety requirements. The battery charge circuitry, the power distribution system. This one doesn't include the solar arrays, but there are options for solar arrays. Along with command data handling. So that's our typical command and telemetry handling system, AES 256 software-based encryption. There's the option to do a hosted payload application where we use one core of our processor. You can have access to the other core to either process or fly other algorithms or other software of opportunity, along with our heritage fault management system, which is kind of one of our strengths. We've got a fault management philosophy that's a little unique. It's very robust, very tested. you get that with this package. For RF communications, radios are always weird. Radios have been a bane of our existence for a long time at Blue Canyon. What we've done is we used to build our own radio. We are now going to go outside and bring in an external radio. We've got a vendor that we've selected. We can either procure the radio for you, or you can procure that radio and do the integration for us. That's going to be standard 100 kilobits per second uplink, 2 megabits per second downlink in the S-band. And it also comes with this, since it's more of a component view, 100 hours of support from us. You can always purchase more support if you'd like, and use it for however you would like it to be used. In terms of payload support, this is a standard offering, so the expectation is the payload will conform to our offering. That is multiple power sources, so we got 12 volt unregulated. We have regulated 5 volts and 3.3 volt services as well. Digital interfaces are UART generally, 3.3 volt, 2.5 volt LVDS, and 422, 485, along with SpaceWire. We are looking at adding some more payload interfaces as we are seeing different people coming up with different ideas. That'll be further evolutions of this avionics. Like we talked about, you can host your payload application on us. We have a real defined API, so you can see how you interact with us. We can provide you telemetry. You can process your telemetry and return it back to us if you would like for downlink. It includes thermal control. This is a software-based heater control. It's got up to 3 heater thermistor pairs that you can use. We'll specify both your survival and operational limits. And that'll be built in. And standard fault management for the payload. Generally, you report to us a fault, we'll power you off and safe you. We will also monitor some of your power services to make sure that, and some thermal services to make sure that your payload is healthy if your software is not detecting it. All right, and with this, there's always options. You buy the car, you get the options as an add-on if you'd like. We don't do undercoding, but we do offer an EDU. This is one that we can get to you early. You can do your payload interface development. Looks just like our avionics. So when you do the integration, it should work very smoothly. You can add a second one of our star trackers, an NST. It's external to the bus if you need 3-axis real precision pointing. You can add 2 more batteries if you're power hungry. Those are 2 3-cell batteries, so you can get all the way up to a 12-cell battery on board. You can add a 4th sun sensor. Typically, people will want to do that if they would like a 4th one for sun avoidance. Launch site support, so we can help with integration and launch site. We can help with dispenser procurement, integration as well. We will help you with reviews. We all know that we have reviews. So if you need support for things like mission level reviews, we're happy to do that as an option. Mission ops, like I said, we can do mission ops. You want to just say, don't bother me with this. I want you guys to operate it. We will do that, give you some really nice interfaces so you can look at telemetry, see what's going on, and retrieve your science telemetry. And lastly, we can add as many hours of support as you feel like you need. It can be by the drop, by the bucket, whatever you would like. Oh, and I should go back. That's basically what the avionics look like. So it's about a 2U package. The red is a removable flight cover that our CAD guys couldn't remove before flight. But you can see the top part is where our avionics, our actuators live. So that's where the trackers, wheels, torque rods all live in that upper slice. And then the lower slice is where the avionics cards and the battery lives. The radio would be external to there. Sun sensors obviously external to there as well. Talking about heritage, we've been around a long time. Like I said, our first satellite was Raven, launched in 2016. We've got 70 plus CubeSats that have flown. We also do minisats, microsats, 15 plus in that area. We've had 190 spacecraft orders, 10 plus years of hardware delivery. Like I said, we've flown particularly the CubeSat form factor in deep space, LEO, and in GEO. We've got a new GEO program starting up here shortly. We've sent our GNC systems to Mars on the Marco mission. Our avionics, you can see 1,300 reaction wheels, tons of our nanostar trackers, a lot of our flex cores. Our flex cores are kind of the larger satellite distributed ADCS system. for your bigger birds. Our exact is our CubeSat system. This is one of the things that we like to bring. We know that as a PI or as a project sponsor, you've spent probably 5 or 10 years planning your mission, trying to get your mission going. We want to be there to help make sure that you're successful. We feel like we have the heritage to prove it. That's what I had. What do you have? I'm happy to answer any questions. I'm really excited about this. I'm a CubeSat evangelist. I really love being here. So let me know any questions you have, and like I said, I'll be around to, yeah, back here in the middle. Yeah, so the question is whether the reaction wheels were 50, they're 50 millinewton meter seconds. Yeah. We have a 15 millinewton meter second wheel out here on display. Didn't have a 50 that came in our package. I wish we had, but it's only slightly larger. And generally, for people that have a good feel, 50 millimeter seconds size wheels are sufficient for almost all the CubeSat classes. When you get to about a 16U, which is a product that we're moving into and there's a lot more interest, you're gonna get probably about 2 to 2.5 degrees per second of slew rate out of that sized wheel, so it's still a pretty capable wheel. Yeah. Yeah, the question, here I'll go back to that. The question is what the volume of this avionics package is. Approximately 2U. Yeah, the question is if we've thought about making the radio swappable. We have, and that's something we can certainly do. Kind of had to settle on one thing to have the right interface and be able to figure out how we were going to test it. So the radio we picked fits, for a little history, BCT used to manufacture our own radios. We're not an RF house. RF houses are way better at making radios than GNC house is. No slight to GNC engineers because I'm a recovering GNC engineer. But we decided, hey, let's leave it to the pros. And we picked a radio that fits basically the envelope that the old BCT radio did. Certainly it depends, and Dr. Lightsey, that there's a wide range of radios out there. So being fully compatible with everyone would be tough in a standard product, but we certainly can talk. If someone has one, we're happy to entertain and tell you if there's any challenges with that radio. Any other questions? Yeah, another question. Yeah, the question for folks who couldn't hear online is whether or not in the pressures and different, we'll call it agendas of kind of the classic NASA DoD space versus university space and the risk postures, if we've considered kind of bifurcating our products to offer solutions that fit both of those. We've talked about it. This is kind of our first best effort at trying to do that. Along with, and I didn't really present it here, we've created kind of standard, you can get the avionics standalone, you can actually progress up to what we're calling an XB1 Plus, which is avionics plus solar arrays plus a standard chassis that then, if you're a payload developer, university, your students can focus on the payload, you can do the integration or we can do the integration if you would like. In terms of trying to figure out how to split the product and beat down one of them to be more risk acceptance and lower cost. It's been a really hard thing, and I've thought about it a lot. And there's a really unique situation with Blue Canyon because we started out with kind of a top tier pointing, and that was the intent, was to bring in GNC experts and bring real world class pointing to the CubeSat market. And then when you say, okay, well, how can I go lower performing, it becomes a really weird maneuver versus if you came in as a lower performing GNC and wanted to go up. It's been a discussion. Right now, it hasn't gotten a ton of traction. Our GNC isn't set up very well for things like a sun sensor magnetometer, triad kind of solution attitude pointing. It itches in the back of my head, so if you have thoughts, I'd love to know how much. All right, I think I'm out of time for questions. We'll be here answering questions, and I appreciate your time. Thank you so much.
Okay, your next presenter will be Alexander Nash and Marco Putnick from the University of Delaware, who will be presenting the design and validation of resistor-based burn wire, a resistor-based burn wire deployment mechanism for the Dapper CubeSat.
Hello, everybody. Thanks for being here today. This is the design and validation of a resistor-based burn wire deployment mechanism. My name is AJ Nash.
And I'm Marco Putnick.
To briefly overview our mission before getting into it, this is the Delaware Atmospheric Plasma Probe Experiment, also known as DAPPER. It is a 3U CubeSat mission based out of the University of Delaware. We will be delivering to the NASA CubeSat launch initiative in August of 2027. This project is funded through the NASA Delaware Space Grant and has been approved through the CSLI as of 2024. The goal of this mission is to map the F2 layer in the upper ionosphere, and we will do that by deploying 2 Langmuir probes, which will measure the average variation in the electron density and temperature there. To overview the deployment system, so the purpose will be to deploy the 2 Langmuir probes outward from the satellite. They will be stowed in the upright position in order to fit on the NanoRacks CubeSat deployer. A torsional spring will be used to provide the necessary torque in order to deploy it outward from the satellite. The probe arm itself will be held upright by a high molecular weight polyethylene line, and this weight will be held straight by a tensioner system, which will then be released through a burn wire release mechanism. So to begin, we had to choose the torsional spring that would be placed in the hinge of our system. We tested 6 different spring-oriented designs for this mechanism. We had to consider the density flux from the impeding forces from the plasma, as well as the Coriolis effect in the atmosphere to determine which strength-rated lines or springs we would need. The maximum torque ratings range from 0.05 inch-pound to 3.509 inch-pound. This is basically just the necessary torque for our spring to deflect to that 90-degree angle that we desired. So we 3D printed 6 different models, and when all things were considered, we went with the 2.679 inch-pound spring. This was mainly due for the ease of use with that level, and also because it was able to hold up our probe arm.
So moving on to the deployment-specific material selection, we had 3 constraints that we took into consideration. We wanted to reduce the chances of cold welding, which is a process that occurs in the vacuum of space between 2 identical metals where they fuse together. We also wanted the material in contact with the probe to be non-conductive, and for these materials to be able to withstand the fluctuating temperatures of the space environment. So PEEK was used for the pin and the washers to ensure that cold welding didn't occur between the metals. PEEK was also used for the collate for that non-conductive side of things. PEEK is basically an aerospace-grade plastic that has a very high thermal stability and great strength-to-weight ratio. It's called polyether-ether ketone. And then we also used aluminum 6061 for the majority of the other parts because of its wide range use in the aerospace field.
Going from there, we had to choose the material for the line that would hold the probe arm upright. So we had to consider some of the following constraints. Firstly, we needed to make sure that the resistor would cause the line itself to melt once we provided it with a current from our power supply. Secondly, we had to make sure that this line would not break under the tension from the probe arm and also not elongate from being in storage, the applied force for a certain period of time. Lastly, we needed to ensure that this line would not be impacted by the ultraviolet light from the sun in the F2 layer. One of the main measurements we considered while choosing this line was the tenacity, which is essentially just the material's strength to weight ratio. So going off those constraints, we came upon the 4 metrics of the melting point, the tensile strength, the elongation percentage, and the ultraviolet resistance. And the 2 materials that we kind of narrowed things down to were spectrofiber, which is an ultra-high molecular weight polyethylene line, and a nylon line. Nylon has been used in lots of previous missions where they used a burn wire mechanism. So as you can see from the table here, spectrofiber kind of trumped nylon in all of the metrics that we were considering for our application.
Once we chose that spectra line, we wanted to ensure that the strength rating was okay. So we tested a range of 10 to 30 pound rated lines. We found that for every 10 pound increase in strength, the burn time increased by 0.5 seconds. While 10 pounds would be okay for use here on Earth, the 20 pound strength rated line was selected to account for some of the unmeasured forces that we might experience, like the prolonged storage of the satellite and the vibrations due to launch. We found that with the 20-pound line, we had a final average cut time of about 4.6 seconds. Then moving on to some electrical constraints, we wanted to be under 0.85 amps because the connectors had a current limit of 1 amp. There was also the constraint of having a 12-volt power supply. This ensured that we had a greater amount of power for a lower amount of current. This gave us the resistance having to be greater than 14.1 ohms and power ratings of about 10.29 watts. Moving on to the cut time, we wanted it to be less than 30 seconds because for a good pass, it's estimated to have communication with the satellite for about 3 to 5 minutes. And we wanted to be able to deploy and verify or confirm the deployment in one pass. On the right side, you can see a zoomed-in picture of the burn wire mechanism for one of the resistors. So power is very important. It was very important in the resistor selection, but we found that power over area, or power density, had a way greater correlation between the mean cut time. We went with a wide variety of resistor specs, the powers being from 2.88 watts to 3.88 watts, resistances ranging from 38 to 50 ohms, and the current rating from 0.24 amps to 0.32 amps. We wanted to also ensure that the operating temperature was greater than 147 degrees Celsius, which was the melting point of the spectra line that we chose earlier. We ended up going with the 38 ohm resistor, and we were a little bit worried in the beginning because we were running more power than it was spec'd for. But after testing it for 20 trials, we realized that the resistance didn't increase by much, so it was okay.
Moving on from the resistor selection, we had to implement a spool tensioner system. So this was done in order to reduce the tension in the molecular line that we were using to hold our probe upright. So basically, the line will be routed around the 2 spools, which should be on opposing corners of our deployment board, as you can see in the picture on the right there. The tension will support the probe arm, which will be located directly in between both of our spools. The ends will then be secured with washers to prevent any sort of slippage that may be experienced during, say, the vibration from the launch. Similar methods have been used in the past, and they were strong motivators for how we came up with this design. Speaking of that heritage, these 2 in particular, this bolt washer concept on the left and this tensioner concept on the right, were used to pretty much come up with our spool type of system. So basically, both of these missions implemented a sort of tensioner that would basically get rid of the tension that the resistor would experience and kind of move it to a different mechanical system. So this was very applicable for us because we were concerned with the resistor possibly coming undone or having too much force from the tension from the probe arm. So now that we've showed each subcomponent and went over some of the heritage, here is everything all together. Yeah, it's deploying. That's a 3D model that we made. One more time. Cool. There we go.
So then moving on to the confirmation of deployment, we're going to be using a linear unipolar Hall effect sensor, or better known as a magnetometer, which can be seen on the bottom right in the red circle. This is going to allow us to confirm deployment by measuring the change in magnetic field strength. And then there's going to be a magnet mount, as can be seen on the CAD model. This is where this will be press fit onto the boom arm, and a small neodymium magnet will be placed inside to be able to trigger that magnetometer.
In the coming weeks, we plan on putting our mechanism into a TVAC chamber in order to see how it responds to the variance in pressure and temperature that we should be experiencing in the F2 layer. Once we do that, we'll just analyze the impact that these temperature and pressure ranges have on the cut time of our deployment mechanism. Once testing successfully completed, we should be ready to integrate it into the rest of our satellite. Before wrapping up, we'd like to give a special thank you to the Delaware Space Grant Consortium and NASA for providing us with the resources in order to pursue this awesome project, and also the Delaware Space Observation Center for giving us and many other students the lab space that we needed in order to complete this. So thank you, everybody, for coming here today. And were there any questions about the presentation? Yep.
In the video of your burn, your test burn there, how long was the burn for that?
Yep, that's a great question. So he asked how long did it take for it to burn. So if I can get the video to go, maybe not. There we go. So we gave power to it around 2 seconds into this video, and pretty consistently it's 4.5 to 5 seconds for it to go. That's with the 20-pound line and the 38 ohm resistor that we ended up going with.
So that was 4 to 5 seconds for it to burn through, right?
Yes, that's correct, sir. Yep. Great question. Thank you. Anyone else? Yep.
How long after deployment were you planning to deploy the sensors?
Do you know?
This is probably more a question for the electrical team, but it kind of has to do with when we're going to have communication with the satellite. As I said before, we're going to have times where we have 3 to 5 minutes of communication, and yeah.
On one of your previous slides where you were comparing the two materials, poor UV resistance can also be viewed as a good backup plan if your burn resistor fails.
Yep, so he mentioned that poor UV resistance could actually be a good thing in case the resistor fails. That is true, but we would rather be confident that the reason it's deploying would be from our own accord with the resistor, and we also want to make sure we don't have a premature deployment via the ultraviolet light from the sun. Did you have a question up here?
No, I was wondering if Vectran had been on your short list, because some people prefer it for dimensional stability over spectrum.
Okay. Yeah, originally that was it was Spectra, and also Dyneema was considered as well as that. But we went with the Spectra, I think mainly due to its higher yield strength than the others. The melting points were both severely lower than nylon, so that was a huge plus for us. But yeah, that was a great question. Thank you.
When dimensional stability is what you're trying to optimize, many people like Vectran.
Got it. Yeah. Thank you. Yes?
Did you also experiment with nichrome as a burn mechanism?
Yes, did you want to talk on the nylon?
Yeah, we experimented with this, and we found that we needed a very long piece of nichrome to be able to reach this amount of resistance that we required. And we found that a lot of resistors are made with nichrome materials. So it was basically doing the same thing, but we found for our application it was easier to go with the resistor.
Yeah,
Yeah, thank you.
Oh, yes. Um, Got it. So he asked about the prospect of using nylon and if it would basically be better in the ultraviolet light or if it would degrade over time. Mhm. Gotcha. Yeah, that's a great question. We originally started with a nylon line, and once we moved from the nylon to the spectra using the same resistor, we saw such a steep increase in the burn time just because of its melting point being like 100 degrees Celsius higher. So we actually didn't even consider the ultraviolet degradation for the nylon, just because the advantage from the melting point was just so significant. But that was a great question. Thank you. Yeah. Yes. A different what mechanism? Gotcha. So he asked about if we found a different way to secure the resistor to the deployment board. I think we just soldered.
Yeah, so basically, that's what the tensioner concept is kind of for. It's kind of relieving the tension on the resistor. Before, we were considering ideas where we would have a line connected to the resistor and nothing to relieve that tension. But we found that, right, like you said, I mean, the only thing that would be helping with that tension would be the solder joints. But with the tensioner concept, it greatly reduced that amount of stress on the resistor.
Yeah, and actually that question was really one of the main motivations for, originally we were going to do one spool and then just have it wrapped to some fixed point. But when we incorporated two spools with a tight knot on each of them, the resistor is really not experiencing that much tension at all. It's really just making contact with the line, which was the intention of the system. So, great question. Thank you. Yes. That was done in air, but in the coming weeks, we will do something similar in the vacuum, in the TVAC chamber. Does that answer your question? Great. Yes? Great. So the question was, did the deployment of the probe cause the satellite to vibrate or change the direction from the mass on the probe? I actually do not know the answer. I don't think there are any variations from that. We're being told that we're out of time, but that's a great question, and that is something that we should probably consider moving forward. So thank you for that. Yep. Thank you, everyone, for being here today, and thank you all for your questions. Appreciate it.
Okay. The next presenters will be Benjamin Kurtz and Drew Stenard Stockton, who are from our own Cal Poly CubeSat laboratory. They will be presenting AmDropSat, a 3U CubeSat to test an additively manufactured deployable radiator with oscillating heat pipes.
Hello, everyone. My name is Ben. I'm from the Cal Poly CubeSat lab.
Hi, I'm Drew. I'm also from the Cal Poly CubeSat lab, and Ben and I co-lead the AmDropSat flight mission together.
Get the clicker.
Kyriakos. Clicker.
I'll go get it.
Sorry, just a moment while we get the clicker.
Thank you.
Excellent. So, with the rising popularity of CubeSats over the past 2 decades, and more complex and thermally intensive avionics and payloads on board, the need to dissipate heat effectively has been an increasing concern for CubeSat developers. To solve this problem, the AMDROP radiator, which stands for Additively Manufactured Deployable Radiator with Oscillating Heat Pipes, is being developed in collaboration with CSULA and NASA JPL. The goal of the AMDROP SAT flight mission is to integrate 2 of the AMDROP radiators onto a 3U CubeSat and test the efficacy of these oscillating heat pipes in low Earth orbit.
Yeah, so as Drew mentioned, we are planning to fly 2 radiators on our 3U spacecraft. And as you can see here, these are both deployable radiators. So in their stowed configuration, they will be part of our 3U structure. And then in the deployed state, they will kind of look like little wings attached to our spacecraft. And as Drew also mentioned, this is a collaborative project. So we are working with Cal State Los Angeles, which has a driving design behind the radiator payload. And then NASA JPL is our providing the primary thermal engineering expertise along with the manufacturing of the radiator. So they're the ones that are actually doing the 3D printing of the radiator out of aluminum. And then us as at the Cal Poly CubeSat lab, we're providing the bus engineering and the spacecraft itself to test the payload in orbit. So that includes the spacecraft structure, all of our avionics components, and flight software.
Yeah, so moving into the general concept of operations for the flight mission. So post-launch, we'll detumble using passive magnetic hysteresis rods and a permanent magnet, which will control our rate of rotation in all 3 axes. Post-detumbling, we'll establish communications. We'll need to deploy our antennas to do that, which includes a burn wire resistor that's been flown on many flight missions from the CubeSat lab here in the past. After establishing communications, we'll do a preliminary system checkout to ensure that our spacecraft is power positive and is performing as expected, and continue to attempt to determine the orbit using data from the US Space Force 18th Squadron space track. We'll then deploy the radiator and complete a system checkout, including looking at our deployment angle sensor data, which uses a Hall effect magnet to determine the deployment angle of the radiator. After we've confirmed successful deployment, we'll continue with radiator experimentation, which I'll talk about more in the next slide. We'll be deploying from the ISS, and so at an ISS orbit with our mass limit that we have with our launch provider, we'll deorbit in about a year. So moving on to that experimentation matrix. So as you can see, we'll first be testing each of the radiators individually. So we'll be doing an increasing amount of wattage to the heaters, which will heat up the radiator and test the ability of the radiator to dissipate that heat. The final test, which is number 11 in the experiment matrix, will attempt to dissipate 50 watts of heat using those 2 radiators. So the key goals there are that 50 watt of heat dissipation, and then demonstrating the effectiveness, the effective conductance of 6 watts per Kelvin across the flexible joints.
Yeah, so given the kind of unique geometry associated with this payload and trying to integrate 2 AMDROPs into the spacecraft, there are some constraints with the bus design. So here you can see kind of an open cross-section of our satellite structure and components with one of those radiators removed. One of the more unique factors in this spacecraft is what we call the battery lightsaber. So rather than integrating our batteries in a more typical fashion of a CubeSat mission, we are running a beam all the way down the length, the z-axis of the spacecraft, and attaching our batteries to that beam. That allows us to make use of that internal geometry while still allowing us to integrate 2 AMDROPs, kind of sandwiching that battery lightsaber. Attached to that lightsaber are not only our battery cells, but also our battery circuitry protection, which is custom developed by our avionics team. And then we also have ballasts attached to that battery lightsaber to increase our spacecraft mass. We're flying at an ISS altitude around 400 kilometers, so we have a relatively low orbital lifetime, so we want to do everything we can to increase our mass and increase our orbital lifetime. In addition to that, we also have a hold-down release mechanism attached to that lightsaber, so that directly interfaces, there's 2, one on each side, one for each radiator itself. That interfaces to the condenser plate of the radiator and allows us to actually control deployment and prevent any premature deployment in the deployer. On the left side, we have our Cal Poly custom flight stack. We call that the top hat. On the top hat sits our flight heritage stack of avionics components. We are developing a custom payload integration board that takes care of all of our data collection for those radiators, So that's things like the actual heaters, the deployment mechanisms, the thermocouples, everything is controlled by that payload interface board. And then what's kind of hard to see, but under that flight stack, we have 2 deployment angle sensing boards. So in those hinges, if you can see kind of those pink and purple hinges that are attached to the radiator on the backside of the spacecraft, we have a magnet. During deployment, that magnet will turn, and we'll have a deployment angle sensing board that can detect that deployment and give us a deployment angle. Another unique part of this satellite bus is that we only have 2 side panels worth of solar cells, so that puts some power budget constraints on our spacecraft. Because the radiators take up 2 sides of the 3U structure, we have limited space for solar cells. We're also flying a couple solar cells on the plus Z face, so that's all the way on the right side of the spacecraft, to try to maximize our solar input. Now, looking at the payload itself, this project has quite a bit of history behind it. Cal State LA has been developing very many iterations of AMDROP. There's 3 main iterations. So the start of AMDROP actually started with 2 plates. So the bottom plate is our evaporator plate. That's where we're going to be simulating a heat load with heating pads. And then the top plate is the condenser plate. So that's what's actually going to be radiating heat into space. Between the 2 plates, we have a couple different versions of tubing that allows the refrigerant to flow between the 2 plates and actually dissipate that heat. In the first version of AMDROP, it featured a spring-coiled tubing system. So the coils that connected the 2 plates were actually what fed the refrigerant between the 2 plates, but they also served as a deployment mechanism. So in this case, the deployment mechanism was actually just a spring force, and our spacecraft would have had to hold down that spring force until deployment. AMDROP 1 did not meet the thermal requirements that we were looking for, so they moved on to AMDROP 2, which expanded the tubing diameter on the inside to allow for more refrigerant flow. While this did help with the thermal characteristics of the payload, there were some issues with the actual stowing and deployment of this version. We found that this version was not capable of being stowed without plastically deforming the tubing. So that led us to AMDROP 3, which is a current design. There have been multiple iterations of AMDROP 3, but in AMDROP 3, Cal State LA moved away from the spring design itself, which also helped us with our deployer integration, because we are no longer holding down all that spring force. So in AMDROP 3, we have standard tubing between the vapor plate and the condenser plate. And alongside that tubing, we have nitinol wires. So nitinol is a memory-shaped alloy. And in this case, that nitinol has a memory shape of 180 degrees. AMDROP 3 is being plastically deformed, so it's going to be physically bent into a 90-degree shape, as you can see here. And then on the spacecraft, we have wires wrapped around all of those nitinol wires that go in between the 2 plates. And when we run current through those wires, we heat up the nitinol. At 60 degrees, that nitinol will want to return to its memory shape and will physically bend the radiator back into a 180-degree shape. So in this case, we don't have any stored potential energy in the radiator, so there's a much lower risk of premature deployment or accidental deployment, which definitely helps us with our risk analysis. So yeah, AMDROP 3 uses that memory-shaped alloy for our deployment mechanism.
Yeah, and so looking more at that AMDROP 3 design, on your left-hand side over here, we have an X-ray of the AMDROP 3 radiator showing the channels that will contain the working fluid. On the right is a sample of the AMDROP radiator. This is now an outdated version, but it is an earlier version of AMDROP 3. And a vibrations test was done here at the Cal Poly Vibrations Lab, mainly to test the effect of the HDRM mechanism on the vibration frequency response on the edges of the radiator plate. So you'll be able to see the metal connecting point on the radiator. In that center is where the hold down release mechanism holds the radiator. And so we were interested in looking at the ends of the radiator and their response. This vibrations test was largely, it went very well. There was nothing of note to report.
Yeah, and then looking at some of the more recent developments to the AMDROP 3 design, which is what we intend to fly. So this is kind of a see-through version or a transparent version of AMDROP. Inside, you can see all those oscillating heat pipes, so that's where the working fluid will be transferred between the evaporator plate and then on the top, the condenser plate. One thing to note is we did extend the condenser plate, so there is almost like a little heel that extends the surface area of the condenser plate to try to maximize our thermal radiation into space. We also LA increased the number of turns and density of those oscillating heat pipes to try to increase the working fluid throughout the system. In addition to that, we have been experimenting, or JPL has been experimenting with different manufacturing techniques. Originally, the design was to be printed in one continuous part that was designed to be printed vertically. That was not entirely successful. There was issues with debris inside the actual tubing inside of the plates. So we moved to a multiple print design. So that featured actually printing the evaporator plate and condenser plate separately, and then brazing the tubing that connects the two onto each plate. Now, the brazing process has also been a challenge. There have been quite a few leaks in those brazing joints when we fill the radiator with refrigerant. So the newest design was shrunk kind of in the x-axis in this image to fit onto a singular print plate where it's now going to be printed horizontally. So it'll be laid on a print plate and printed in one continuous piece, which should hopefully improve our manufacturing processes. And we are currently working with JPL to get initial testing units that can be tested in our space environments lab, and then move forward to getting units that can be put on our engineering test unit and flight unit. We're looking to have our flight unit tested, or the flight unit radiators tested by the end of 2026.
Yeah, so finally moving into that path to launch, as Ben started to mention there, the next thing that we're looking forward to doing is receiving that initial test unit radiator, where we'll be doing a vibrations test and a vacuum test with the working fluid in the AMDROP radiator here on campus. Additionally, thermal testing of the radiator, of the initial test unit radiator, and then the engineering test unit and flight unit radiators will occur at CSULA, along with mechanical tests at CSULA to test the deployment force and ensure that full deployment of the radiator is possible. Integration and qualification testing will happen here. We'll be able to test the full engineering test unit with our avionics stack up, and then test the entire flight unit, going through environmental and qualification testing there. Our planned launch is in early 2027 to the ISS, so we're looking at a handoff date in December of 2026.
Yeah, we'd be happy to take any questions. We are also outside in the lobby with a version of AMDROP that we did some testing on. So we'd be happy to take any questions here, or also you can come by and stop and see our payload. Yeah.
Did I understand you to say that JPL is not only 3D printing the plates with the capillaries in them, but also the tubing, or is the tubing introduced later in the brainstorm?
Yeah, so the tubing, if I can go back. So the tubing that connects the two plates in this image, there have been a couple different versions. Some of it was initially the top and bottom plate were additively manufactured, and then the tubing was stock material that was brazed to connect the two. In more recent versions, those tubing joints have been, or the tubing itself was printed, so the whole thing was additively manufactured and then brazed together. And now in the most updated version, it's being printed all as one piece.
I was just curious what refrigerant you're using and what is the thermal effectiveness? Like how many watts of heat can you radiate?
Yeah, so there have been a couple trade studies to look into the refrigerant. That's mainly a decision on the LA and JPL side. The current plan is to use R134A. And as Drew mentioned, the goal of this radiator is to dissipate 50 watts of heat. So if we go back to the experiment matrix, at the very bottom there, you can see we have 2 heating pads per radiator. Those are simulating our thermal load. We're looking to dissipate 50 watts of heat at one time with 2 radiators. And we're kind of working our way up to that. First, only testing one radiator at a time, and then towards the end, testing both radiators at the same time.
Yeah, so that's been an issue in the past. So one of the issues with the Nitinol deployment is it's largely dependent on the diameter of those tubes. And so there's been quite a lot of testing at Cal State LA to determine the correct diameter of tubes that allows for the Nitinol to fully deploy the radiator, so for the radiator to not be too stiff. The current design is based on those trade studies and based on the testing to see what the appropriate outer diameter is of the tubes to confirm that the Nitinol can deploy the radiator all the way.
There were also some challenges kind of figuring out the right deployment or transition temperature for those Nitinol joints. Initially, LA had chosen a Nitinol that transitioned at 40 degrees Celsius, which, although worked well for our power budget because we needed less power to actually deploy the radiators, we saw that on orbit, it's possible for our deployer temperatures to reach over 40 degrees, which means that the ambient temperature of the spacecraft would deploy the radiator prematurely. While we do have a hold-down release mechanism to prevent that, we didn't want to rely on that fully, so we increased the transition temperature up to 60 degrees Celsius, which means that the radiator should really not be able to deploy unless we put that heat into the Nitinol. Yeah, so for leaks specifically, we do have a couple procedures on the testing side. Some of our first tests that we're looking to do once we get a fully charged version of Amdrop in a couple weeks here is to do basic vacuum tests and vibration testing. That vibration testing is mainly to check for any leaks. We do have access to a refrigerant sniffer, so that's mainly a piece of safety equipment to make sure that we can detect any leaks of that refrigerant, but we also have pretty diligent procedures that include weighing the radiators before and after all of our testing to detect any leaks. In terms of deployment cycles, we were given anticipated numbers from JPL and LA about how many deployment cycles these can go through before they fatigue and start leaking. So we're gonna have to do some testing on that, and that will kind of address on how many deployment cycles we can put through our flight unit.
Great. I think that's all the time we have for questions, unfortunately, but we do have that booth upstairs with that model of Amdrop, so come talk to us and ask any more questions you have. Thank you, everyone.
Well done, guys. That was impressive.
I'm super excited for the Amdrop work and the upcoming launch. Next up, from the US Naval Academy, we have Garcia, Hardaway, and Williams, and they're going to be speaking about CubeSat on orbit separation mechanism development. Let's please give them a warm welcome.
Excellent. Hello there. We represent the United States Naval Academy.
I'm Midshipman Nadia Garcia.
I'm Midshipman Mac Williams.
And I'm Team Lead Midshipman William Hardaway. We're here to present to you the SPLITS subsystem. So a little bit of background. SPLITS itself is a independently operational separation and ejection sequence for 2 CubeSat systems. It'll be integrated onto the BEARSAT mission, which is a joint mission between the Naval Academy and the Coast Guard Academy to create CubeSats that can be placed into low Earth orbit and a polar orbit to support search and rescue operations in the Arctic and Antarctic regions. SPLITS itself will be supporting this mission and also producing an on-orbit demonstration of its capabilities for future scalability and other CubeSat applications. It offers the capability of creating low-cost, scalable, close proximity orbital constellations for CubeSats that can benefit missions such as ISR, where a lead satellite can queue a follow-on satellite for further investigation, or scientific experimentation that requires near-simultaneous data acquisition of a local field. Slide, please. So there are a couple different problems that SPLITS has to overcome. The first being maintaining structural integrity between two independently operational satellites during the launch and G-load sequence. The other being it has to be small enough such that it doesn't infringe upon the payload space of the CubeSats it's operating between. And then finally, the separation sequence itself has to be conducted in a controlled manner such that it doesn't damage either of the satellite systems. Slide. Before iterating upon our own design, we investigated previous solutions to docking and separation. Most of these consisted of cup cone docking systems, latch release mechanisms, and mechanically actuated springs. All of these systems were integrated onto far larger and more complex space infrastructure systems. Slide, please. Our goal was to scale this down to a CubeSat level that was able to be simple enough and cheap enough that we can use it on the university and CubeSat scale. This included ensuring, once again, the separation was safe and secure during the launch sequence, such that we can have two satellites that are independently operational, both in the conjoined and separated state. And finally, making it simple and cheap. Slide. All this would be executed over our ConOps, where they are conjoined prior to integration into the launch vehicle. Following launch and deployment, both satellites will turn on and begin communicating with our ground station, where they will begin executing their mission set. Then, at a desired time, our ground station will issue a command to begin separation of the two satellites. Following separation, the two satellites will once again continue their mission operation. Slide, please. Our proposed solution for the system is twofold, both an ejection and a separate separation sequence. The ejection will be handled by a spring latch bolt, which is activated by a burn wire. The spring latch bolt provides the tensioning force that creates the structural stability and integration between the two satellites. Following the burning of the burn wire, that spring latch bolt is released, and the two satellites are now free-floating next to each other. The solenoid element consists of two concentrically located solenoids at each corner of the satellite. These solenoids are wrapped around non-polarized steel, such that when they activate, they'll be magnetizing those steel rods, creating an opposing polarization that then creates opposing magnetic ejection force. Slide, please. This is a basic graphical image of what the satellite looks like. There are two 3U systems. Both satellites will have a bottom U, which is the Naval Academy standard bus. This will be providing the power, comms, attitude, and control of both of the satellites. This is then hooked up to the top 2 U's of both satellites, which consists of the payload. In this case, the BearSat payload and the U.S. Coast Guard's search and rescue equipment. The split system is then leveraging a lot of the exterior space within the 6U deployer that links the two satellites together, with the central bolt element that maintains structural integrity in the center, and then the 4 concentric solenoids located at each corner of the 2U system. Slide, please. This is a basic image of our simplified CAD diagram, as well as images from our integration test. It provides further illustration of where the forces are being applied, once again with the central bolt providing that tensioning force, keeping them together, and then the solenoids with their own cup cone systems providing stability, and then finally, when the solenoids are energized, that ejection force necessary for separation. Slide.
So we had 4 key system requirements. The first was maintaining structural integrity during launch, being able to survive the vibration forces of launch. The second one was that we need to achieve a minimum separation velocity of 1 centimeter per second. This is to prevent the satellites from reconnecting due to atmospheric drag or other perturbations without having too much force that's going to destroy the satellites when they separate. The third is a relative angular velocity no more than 6.8 degrees per second. This is to prevent them from rotating and colliding when we separate. The final one is that we need to operate within our power budget of 4 watts for a duration of not exceeding 120 seconds based on the NASB. Now we'll go over the design details of our few subsystems. The first is that bolt system in the center. There's the big latch box. So there's a spring-driven latch that holds down an L-shaped block, and that latch is held in place by a burn wire, which is a fishing line, and it's attached to a resistor. So when we decide to separate, we'll have electricity flowing through a resistor. It heats up, it separates the burn wire, that releases the L-shaped latch, and then there's a square rectangular turnbuckle in between with 2 reverse-threaded bolts, and that allows us to tension the satellites together externally using like a wrench instead of putting screwdrivers through, conserving space. Next is the solenoid system. So you can see the CAD drawing on the top and the actual one, the prototype model on the bottom. And also the cup cones, which prevent shattering during launch. For stage 1 and 2, they'll be docked. This is what it looks like when it's docked. Again, the cup cones are interfaced together, and then the turnbuckle in between is maintaining that pre-tension. And as you can see, it's relatively easy to access, again, conserving space. Our stage 3 is when we separate. This is what it looks like after separation. So as you can see, the L block there has been released by the internal spring latch, and then the solenoids are separated as well. Again, for the separation ConOps, we initiate the separation command via the CNDH, which we'll talk about. The solenoids pre-activate, so it provides extra tension while the L-shaped bolt is released. And then after the burn wire is separated, then they will reverse polarity in order to separate the satellites.
The command and data handling process controls the entirety of the separation system. A command signal will be sent from the ground station, which is located on Naval Academy's campus. That command signal will reach the Naval Academy standard bus, also known as the NASB, which will receive, verify, and relay that signal to USNA separation system and subsequent U.S. Coast Guard payload. The NASB will log and downlink critical telemetry such as separation status, timing, and overall system health. So separation status will be determined by continuity checks. There will be an initial check upon orbit where we will determine whether or not the satellite has maintained positive contact post-launch, and then as well as a final continuity check after the system has finished its separation sequence. Next slide. The electrical power system supplies required power to each subsequent system in the separation scheme, and you'll see that on the left-hand side, all the power requirements used for the command sequencing on orbit. Our energy will be derived from solar panels, and that energy will be distributed and regulated by the PIB to our custom board known as the buckboard. That buckboard will then downstream the power to subsequent systems. The buckboard itself is like an execution hub. It ensures that the correct voltage is provided, the correct power, as well as the timeliness of that power. Next slide, please. The electrical interface encompasses the following separation sequences, such as the continuity check, solenoid activation, the polarity reversal of the solenoid, and a burn wire release. The buckboard, along with our software, work together in order to provide precise timing, control, and verification of the power throughout the entire separation process. Our software is simple and user-friendly, so the ground operator located at our ground station at Naval Academy will be able to easily interface with our system. Here are some key board components, such as our Adelogger, which is our microcontroller that will process our commands, the H-bridge, which is in charge of solenoid activation as well as polarity reversal, and switch, which will determine when the solenoid and burn wire will activate. Next slide, please. So as you see here in our real-time GIF is solenoid testing, and we were able to successfully generate repulsive force from reversing the polarity. As for our burn wire mechanism testing, we wanted to ensure reliable and timely separation of that mechanism, and we were able to successfully detach the latch in about 3 seconds with 1 second of command buffer. In conclusion, our design provides low-cost, reliable design with minimal moving parts. This improves accessibility to universities as well as reducing overall complexity. Our testing proved that our design works as intended. However, we will continue to iterate and make adjustments as we continue to test and prepare for full integration. That is all for us, but we do have a QR code if you would like to visit our USNA Space Systems Laboratory for more information, and we'll now open the floor to questions. Thank you.
Yes. So mainly like attitude determination and control, ensuring that they stay in the same range within one another. Generally not. It is a dummy system, so once they separate, they'll just be free floating. We have magnetic controls that'll align them, but they'll just slowly be drifting apart. Could be a follow-on for future applications, though. Thanks, sir. Yes, sir.
I was just curious, is it two 3U CubeSats, and then do they fit in a 6U sensor?
Yes, sir. So the question was the precise sizing of the satellites itself. There are two independently operational satellites conjoined together. They're each 3x1, making a total of a 6U satellite system, and it's leveraging the space in the deployer that has roughly 26 millimeters of space between those satellite slots, and that's where we're putting those cup cones in that spring latch system. Thanks, sir. Oh, go ahead.
Yeah, as shown in our testing, we're using 2U skeletons, and then later on attaching the NASB 1U.
To the bottom, yes, sir. Do we still have a question over there, sir? Perfect. Yes.
So critically, is it possible to be utilized multiple times, or is it just a one and done, you separate and never come back together kind of?
So the question was, is this system capable of redocking, essentially? The current iteration, short answer is no. We don't have propulsion systems on board the BearSat. Once they separate, we have no means of rejoining them together. If there's a partial separation, our system includes an H-bridge, which reverses the polarity of the solenoids. It's part of our ConOps operations, where before the burn wire is activated, we have the solenoids creating an attractive force with one another, such that after the burn wire actuates and the spring latch is removed, the satellites remain conjoined with each other. Then we reverse the polarity and create a repulsive force. So theoretically, if we have a failure of separation and we want to just bring them back together, we'll send a command up to reverse polarity one more time and bring them together. That could also mean that we're trying to separate fully again. Thanks, sir. Yes? So just to clarify, sir, the question is, like, how are we finding the precise amount of power necessary so we're not, like, overburdening the system? I would say, like, the sizes of the solenoid. Sure, okay, the solenoid sizes. That was more determined through iterative testing as to what we had some mathematical models of the forces that we were hoping to generate, just because of actual creating it ourselves. Those didn't always line up perfectly, so the end result was namely that we have a certain amount of power that we can supply the system, and just matching the solenoid sizes to the resistance of the wire necessary to create the output current that we want through the wire, namely 0.5 amps with a 7.7 volt system, so just matching the resistance to that. And I believe we're out of time. Thank you so much, and we look forward to speaking with all of you more.
All right, so that's the end of our first session. Now we have a lunch break, a couple more quick announcements. We do have some merchandise, including Hawaiian shirts for sale, up by the indoor registration booth, so go check out the shirts and the bibs. Lunch should be served right around noon out front in the pack, and the second session will start at 1 p.m. Enjoy your lunch.
welcome back from lunch. We will be starting our next session, session 2, involving radiation and space reliability. Our first speaker is going to be Saurabh Kuje from Advanced Cooling Technologies, and he will be discussing a spot shielding approach to radiation and thermal management for CubeSat COTS electronics. So please give him a warm welcome.
Good afternoon, everyone. This is Saurabh Kuje from Advanced Cooling Technologies, and I'll be presenting a 3D printed lightweight radiation shield for commercial off-the-shelf electronics with integrated heat management. So this is how I'll structure the talk. We have problem and motivation, then how we address that problem by defining our solution concept, and then I'll go over technical validation on how we tested these materials for real life conditions, and then I'll follow up with summary and a brief path forward. So this is the background. So space or small sets have been increasingly relying on commercial off-the-shelf electronics since they are cheaper, faster, and more traditionally available compared to traditional space qualified components such as rad-hard electronics. But you see, space is a very harsh environment. So as space constantly experiences the flux of protons, electrons, galactic cosmic rays, and all the other types of radiation. So what we did was we created a dual layer architecture, which I'll talk about in the next slide. So traditionally, before I go there, so the figure on the right shows the radiation exposures as we go from lower Earth orbit to higher orbits, and you can see the feasibility of COTS and rad-hard electronics goes on decreasing as the cost goes on increasing. So traditionally, these limitations are addressed by aluminum shielding, but it has some caveats as the thickness of the aluminum shielding depends on the most sensitive component to radiation, as well as it has a higher mass compared, which increases the swap penalty. It also has poor electron attenuation, especially pertaining to lower energies. And it is also not conformal to complex geometries. What I mean by that is I have a figure I'll show up in the later slides. Whoops. And on top of that, since we are using commercial off-the-shelf electronics, they are increasingly getting more powerful day by day, and hence they generate more heat. And this heat needs to be dissipated through the circuit board, and hence it may cause some localized hotspots. And to address those hotspots, we have the second layer, which I'll talk about in the next slides. And hence, we have two challenges: the radiation shielding and thermal management. So moving on to the solution concept. So this is the concept in brief. We have a dual layer architecture. We have a radiation attenuation layer, which is on the top. It consists of metal oxide particles inside a polymer. And then the second layer is the heat dissipation layer or fiber reinforced polymer composite. It consists of carbon fibers ranging from several hundred microns within the same polyurethane polymer. And we have some metallic particles to create bridges so that the thermal path can be consistent. So, and since this is 3D printed, it can conformally sit on the geometry, and we can utilize that technique to create a spot shield. So instead of having a full enclosure like aluminum, we can have a localized shielding, and hence that enables us to save weight. So this is the functional mechanism. So like I mentioned, we 3D print this, and then that is the schematic of the architecture, what it looks like. So the MOPC or metal oxide polymer composite layer consists of high Z, or Z being atomic number, high Z atomic number metal oxide particles, and it enhances photon attenuation, especially gamma and X-ray shielding, because when radiation interacts with this material, the high atomic number increases the probability of these interactions, and hence it attenuates the radiation. And since it is also embedded within a polymer, and polymer contains hydrogen bonds, they help with protons and electron shielding, as when they collide with the hydrogen nucleus, the protons and electrons transfer energy to the atom, and it's dissipated that way. And the benefit of using this is, unlike aluminum, these architectures do not create or create very little secondary neutron radiations. And then going on to the FRPC, which is the Aligned Carbon Fiber Network, it enables efficient in-plane thermal heat spreading. I'll talk about that in the FRPC slide. So what this is it's a multi-layer architecture that enables simultaneous radiation protection and thermal management. So moving on to the technical validation, where I'll talk about, I guess, okay. Fiber reinforced polymer composite. So the goal is to enhance in-plane thermal conductivity, since this is supposed to sit directly on the COTS electronics, and it has to be not short circuit the COTS part, as well as it should have enough heat dissipation so it can not create localized hotspots. So this is the schematic. The black bars represent carbon fibers, and these are aligned due to the 3D printing. We used extrusion-based direct ink writing, and since it's extrusion, they align due to shear forces, and the metal particles are thermal bridges. Instead of driving the heat through a low conductive polymer, low thermal conductivity polymer, we use metal particles to create a bridge, and hence it forms a continuous low resistance thermal route. And since we also measured the electrical conductivity, it falls somewhere between an insulator and a semiconductor. It forms an electrostatic discharge path. And because it is aligned in plane, it creates a high anisotropy, which means in-plane thermal conductivity is higher than cross-plane. And the takeaway is in-plane thermal conductivity is higher, like I mentioned. So this is the main meat of FRPC. The figure on the left shows the printing process. Figure C shows the planar view. We used optical microscopy since we didn't have access to SEM at the time. So figure C shows the planar view, and it shows the carbon fiber alignment direction vertically. And figure D shows the cross-sectional view, where it shows the carbon fiber alignment along the horizontal direction. So this was 30 volumetric% aligned carbon fiber in polyurethane, and this results in a thermal conductivity of 3 to 4 watts per meter Kelvin. And since we optimize the printing process, the whole print is bubble-free and high quality. It meets NASA craftsmanship standards. And then, like I mentioned, it has low electrical conductivity, 8.8 times 10 to the negative 5 Siemens per centimeter. And this enables thermal dissipation without electrical shorting. And since we use polyurethane, which has a tendency to cure, we did some in-house chemistry. I cannot mention the chemical name, but it gives us a prolonged printing window of more than 80 minutes without the needing to heat the extruder. So this is the thermal conductivity testing. So we tested the thermal conductivity relative to the print direction, since this is how it will sit on the commercial off-the-shelf electronics. So for the base polymer, which is the control, we got a 0.66 watts per meter Kelvin. And then this was a DOE-funded phase 1 and phase 2. So over the years, we kept improving the recipe, and we ended up with 43 weight% carbon fiber loading, which gives a thermal conductivity of 3.8 watts per meter Kelvin. And strong anisotropy, which means in-plane thermal conductivity is higher than cross-plane. And this is comparable to commercial thermal interface materials with added benefit of being printable. And this is the real-life testing that I was talking about. So what we did was we created an in-house setup, and we used a Raspberry Pi 4 Model B as our test setup. And we put the whole shield, the white layer being the MOPC and the FRPCs underneath that. We put the whole shield on the Raspberry Pi, put the whole thing in an aluminum chamber, and created a thermal vacuum, and applied a heat load of 5.1 watts. So the figure C shows how the shield performs, or the FRPC performs in particular. So with a shield, the PCB reached a temperature of 57 degrees Celsius, which is 7 degrees Celsius lower than the COTS without shield. So this means that integrated shield improves thermal management under vacuum conditions, and this is important since in vacuum you can't have convection. So FRPC works. Now moving on to MOPC. So the goal for developing metal oxide polymer composite was to have equivalent radiation attenuation at a lower mass compared to aluminum. So we used a low Z base polymer, which has hydrogen atoms, and hence it can help with protons, electrons. And we have high Z metal oxide particles, which can help with gamma or X-ray radiation attenuation. So in terms of materials, we tested tungsten, gadolinium, bismuth, and we settled on gadolinium. And then we realized gadolinium is very expensive. So what we did was we ran some Monte Carlo N particle or MCNP6 simulations and found out gadolinium oxide or tungsten oxide perform similar, if not better. And I'm sorry, they also are pretty cheap compared to pure metal counterparts. And this composite design leverages high Z attenuation with lightweight polymer matrix, the polymer being polyurethane. So this is the MOPC processing and interface optimization. So this has two parts. The figure on the left shows the printing process, and figure B shows the planar view, and figure C shows the cross-sectional view to show that it is bubble-free. And then the figure D, since earlier we were just doing mechanical mix, the metal oxide particle has a tendency to agglomerate, and hence it does not properly disperse within the polymer. So what we did was we surface functionalized the metal oxide particles with polydopamine, and then we surface functionalized that with silane chemistry, and we were able to create bonds, covalent bonds when mixed, when this functionalized powder is mixed with polyurethane. It can create chemical bonds as well as mechanical bonds. And to prove this system works, we tested 3 samples each of pure metal oxide and surface modified metal oxide. And this is the average result. You can see we got a 31% increase in ultimate tensile strength due to surface functionalization. So far we managed to load, increase the metal oxide loading to 30 volumetric percent, which translates to 75.8%. We are still trying to optimize this and go as high as possible in terms of loading. So this is the radiation attenuation performance. We've validated this using 2 methods, experimentally and computationally. For experimental method, we tested 6 samples each of non-functionalized metal oxide polymer composite in a cobalt-60 gamma reactor, and we tested 3 different types of radiation doses, 200, 400, and 600 kilorads, and a control for baseline. And we found out after 6 tests of each, the average tensile strength remains 2.3 megapascals, which is good since these shields don't only have to shield against radiation, they also have to withstand handling, and polymer degradation can be avoided since polymers are susceptible to radiation. They lead to chain scission. And then for computational validation, we ran MCNP6 modeling. So as you can see in figure C, in lower energy regimes of gamma energy, gadolinium oxide and tungsten oxide perform much better. They have a mass attenuation coefficient of 7 times higher compared to aluminum. And then in figure D, it shows that at similar weight, MOPC can more effectively reduce total ionization dosage compared to aluminum, or you can get, or conversely, you can get equivalent radiation protection at a lower mass compared to aluminum. Moving on to prototype fabrication and testing. So this is the weight estimation, the main part of swap. So we estimated MOPC spot shielding weight for Quartz Electronics, assuming 1,000 rats per year. And then spot shielding enables significant weight reduction versus full aluminum enclosure. So this is what I was talking about in figure B. This is how Quartz Electronics are typically shielded with aluminum. And as you can see, there's much open space on the top, and hence heat cannot be dissipated properly or effectively. So we put a spot shielded MOPC, which was around 3 millimeters thick. It weighed around 22 grams. And then if we add a 3 millimeter thick FRPC as well, we get a total shield weight of 45 grams. So if we compare it to aluminum, we get 70 to 85% reduced mass or weight reduction. And the top row shows our configurations. We have figure A. In figure A is a casted part. Figure B is also casted, is more typically spot shielding. And figure C is the printed part. As you can see, we have MOPC on top of the FRPC layer, and they both are sitting conformally on the COTS electronics. And then moving on to TVAC and outgassing. So we followed ASTM E595 for outgassing parameters. We had a vacuum of 5 times 10 to the negative 5 torr and a duration of 24 hours. And we tested 2 temperatures. We tested 125 degrees Celsius as well as negative 20 degrees Celsius. And the passing criterion for ASTM E595 is the total mass loss should be less than 1%, and the collected volatile condensable material should be less than 0.1%. And as you can see from both the outgassing results, we pass those criteria or meet those criteria. And then we also ran orbital simulation in-house using a thermal vacuum chamber. So we did some accelerated thermal cycling from negative 20 to 125 degrees Celsius. And so far we have finished 500 cycles. And when we took the samples out after 500 cycles, we observed no degradation in adhesion, structure, or electronics functionality because the Raspberry Pis were still working. And our plan is to finish 1,000 cycles, and after that we plan to test thermal, mechanical, and electrical properties to see if the material still holds up. And in summary, so quickly we developed a lightweight dual layer radiation shield for COTS electronics, and we validated the concept with growing commercial and flight interest. So for highlights, we developed MOPC, surface functionalized it, and increased the metal oxide loading from 19 to 30 volumetric percent while maintaining printability. For FRPC, we reached a maximum thermal conductivity of 3.8 watts per meter Kelvin. We are still working on that to see how far we can go. For testing, we completed total ionization dosage under cobalt 60. We also passed outgassing, and thermal cycling is still going. And in terms of modeling, we did Monte Carlo for gamma radiation. The next step is to do it for electrons, protons, and heavy ions. And then we are currently advancing space qualification. We currently have a flight demonstration opportunity with the University of Alabama, as they have a NASA flight club. And it's supposed to fly out this summer, so we are working with them, and partner engagement for commercialization. So currently this technology is at TRL 5, and with flight opportunity, we are confident we can push it to TRL 7 or above, combined with the electron, proton, and other higher gamma dose testing. And this enables slow swap, thermally integrated radiation protection for next generation of space electronics. Thank you. Yes. So the question was, what is the business model? Are we selling the paste or are we selling the service? So that is a good question, because currently our higher upper management is debating on what to do. Some people are saying we sell the printers with paste, and then we go on site and then teach them how to do it. And some people are saying we get the electronics, make the thing, and then ship it back. But again, that creates contamination issues, because currently we do not have a clean room. So currently that's under debate, but the majority people are aiming towards selling a printer with paste, pre-made paste. The question was, can the paste be used with standard industrial dispensing machines? The answer is yes, because the chemical agent we use can be used to modify the viscosity. So depending on what viscosity your machine uses, we can add that chemical and tune the viscosity as needed. Yes. I would say if we do just a regular top figure, it would go between $200 to $500 per piece. Again, that's an estimate. But if we do surface functionalized one, which has a, yeah, this thing, it will be a bit expensive. I think it will be 1.15 times more expensive because this surface functionalization takes 3 days right now to make a batch of 50 grams. Mhm. Yes. The question was, we are focusing on total dose and if it helps with SEU or other types of radiation. My question, what is SEU? I do not. Oh, okay. We plan to test for that. We are looking for third-party vendors that can help us assess that because right now we just finished phase 2 and we are looking for further testing. So that will be addressed when we get there. Yes.
It's an observation, and other people in the room may answer this, I don't know. When you've got a, I don't know, chip, NVIDIA chip, and if you send high-speed charged particle at it this way,
Mhm.
you have less chance of hitting a transistor than you do if you shoot it this way.
Mhm.
I don't see building up around, this would seem to be a very vulnerable plane, and this would seem to be a less vulnerable plane. In 3D printing, it would certainly be easy to accommodate
Mhm.
that by building up around the edges of your chip as
Mhm.
opposed to this. Have you given that any thought? Do you regard that as a real effect?
Yes, because the current opportunity we are working with University of Alabama, the NASA club requested that we provide a sample that covers the whole. Currently, they are using a RunCam splitter version 1.4, I think. So they asked us to give a whole enclosure of this MOPC. So yes, we are considering that.
Is that published, or is ACT engaged in that, and will you be documenting that, or
So,
documenting that?
so the question was, has this been published or is being documented? So we published some work pertaining to this MCNP modeling and the FRPC this thing. The rest of it we filed a patent to protect the IP, and so we are waiting on that still. Thank you.
Awesome. Thank you, Saurabh, and great job and great questions, everyone. I'd like to welcome our next guest speaker, Alexander Jackson from Missouri S&T. We'll be talking about integrated multiphysics simulation and MDAO-driven design workflow for the Dexter mission.
Okay, yeah, thank you for that introduction. As she said, I will be talking a little bit about the design of our Dexter CubeSat mission from the Missouri University of Science and Technology Satellite Research Team. So a little bit of background. On March 4th, 2024, I had the privilege of coming out to beautiful California, just a little bit south of here, and watching the launch of our first CubeSat from Missouri S&T, a mission called M-Cubed. That was really cool, and we had a 7-day timer, and after that 7-day timer, we never heard from our satellite. So then we started looking into it, and we started doing a root cause analysis, and we determined that it was because of a disconnect between our simulation of our communications and our orbital simulations. So obviously that sucked, and the question was, how do we make this not happen again and make the next CubeSats that Missouri S&T launches work? Like I said, we did a root cause analysis, and while the surface cause was that disconnect between our simulation, we found much deeper issues that existed in our team. Those were fragmented tool chains, mismatched analysis parameters between the two simulation software. Late discovery of critical issues on that mission was also a problem. We had to do some really expensive changes right at final integration, and we found that a lot of that was because testing was delayed until the system was fully integrated because we didn't have the tools to test at the component level. And this is kind of illustrated in that graph that I'm showing on the right of the cost of change curve. This is from the NASA Systems Engineering Handbook, and it just shows that the later you have to make changes in the mission, the more complexity and cost that gets added. So we went twofold. We wanted what is the technical approaches to addressing this, but also what are the cultural changes to addressing this. So the cultural changes were harder to get down to the root of it, but we think really important. So test and run analysis as early and as often as possible, starting with the smallest testable unit and working up from there. And when you do those tests, identify all the parameters that you were using in that test or simulation, and then most importantly, test like you fly. Test every single element like it will be used in flight, so we don't get another disconnect like what happened with M-cubed. So then the methodology and tool changes for future missions, we started looking into different strategies that exist out there in industry, and we came across multidisciplinary design, analysis, and optimization, or MDAO, which is in the title of this presentation. And this is a concept of analyzing all the different subsystems simultaneously in a unified framework, iteratively, and then a formal optimization process is also included in this. So those are the three parts of it. Interdisciplinary collaboration, so we're analyzing not just thermal, not just our GNC, but everything all together and sharing the parameters between them. This is an iterative design process, so instead of having to get it right the first time and it sucks to rerun hour-long analyses, you can do rapid iteration through this. We still sometimes get stuck with long analyses, but it's not prohibitive to rerun those. And then the optimization algorithm is not something that we've currently focused on a ton right now, but it is definitely something we want to look into in future work, picking exactly what is the optimal design for a specific mission. So we started looking into it, and there are a couple commercial options that are available, like OpenMDAO, which was originally created by NASA, and Model Center, which was created by ANSYS. And those do really good at the formal analysis and optimization, but they just take in the inputs from other tools. So that's when we came across Warpware with a connection back to Missouri University of Science and Technology, and it fit right in what we wanted to do, and it came at the perfect time just following M-cube's launch. So this is a spacecraft-specific unified framework for analysis. So Warpware has three major parts. There's Warp Twin, Warp OS, and Warp Link. Warp Twin is where you do your modeling and simulation. This is similar to like STK, but what we really like about it is that it links into Warp OS, which is the embedded software. This is where you do all of your GNC algorithms, all of your embedded flight code, state machines, different things like that, and they're meant to work together, so you can actively just flow it right back into Warp Twin and see what your state machine is doing. And then the third element is WarpLink, which is built on OpenC3's Cosmos, and but again, it's customized to work with the other two software. So you can practice sending ground commands before you're in space, and it will be working on your actual flight executable, and you can visualize what that would look like in orbit using Warp Twin, and you can simulate the inputs using Warp Twin as well. So what we really liked at S&T for Warpware was we're a university team, so simplicity is a big thing, especially being mainly aerospace engineers. Software is really scary. So we have a simple yet capable interface. We're not making any compromises on what we can do with the software. There are existing architecture and apps that we can just reuse without having to develop them from scratch. We only have to learn one architecture. It's a full encompassing architecture, but students can focus all of their efforts on this architecture. And then it also enables that early analysis and testing that we identified as a key reason why M-Cubed didn't succeed. So some differentiating factors that make this happen are the application abstraction layer, which is why you can run it in the simulation world and with actual hardware. The same apps, is what they're called, can be run across a wide variety of interfaces. So that includes your GNC is not hardware specific, one specific star tracker, but it's just put in a star tracker. GNC algorithms and sensor driver libraries is really helpful. That's what I was saying. We don't have to start from ground zero when we're developing new Kalman filter type things for navigation and guidance and control. And then finally, embedded software is integrated with the simulation, so we can run our actual flight software and see what it's doing in a simulation. So that brings us to Dexter, which is the next satellite that Missouri S&T is working on right now, and that I serve as the chief engineer for. So Dexter stands for the Doppler Experiment for Search, Tracking, and Rescue. It's a 6U CubeSat designed to do single sensor Doppler-based geolocation and bidirectional communication with a search and rescue beacon. The major challenges with this is we want to maximize the amount of time that we are receiving emergency beacons, because this directly relates to how many lives can be saved, or the process can be accelerated from receiving these search and rescue beacons. We also want to do all of this processing on board, because that's our differentiating factor between the existing technology and our current satellite. And we want to be able to do this in a single pass so that we can downlink this information back down to the end user that would be experiencing the emergency. To do this, we need high accuracy frequency measurements on board the satellite using a custom designed payload that's being made by S&T. And then obviously the challenge that every university team faces is we want to lean into rapid development to combat that continuous personnel turnover. We found that if you can pass it down to one person or 2 generations of passing down this knowledge, that's where you hit your peak. Anything past that, when you're passing it down 3 or 4 times, missions tend to have less mission success. So a timeline for Dexter. This all started in spring 2023 when we met with NASA Goddard, and we got through the initial funding phase. We explored it for a summer with some preliminary funding, and then we got into Air Force Research Laboratory's Nanosat 12 competition in fall of 2024. We had our conceptual design review and system requirements review, preliminary design review. I'm here now at CDW, and we have critical design review this fall with flight selection in January of 2027. So some early design and trade studies that were enabled by this multidimensional analysis and optimization, or multidisciplinary analysis and optimization technique using warpware. I want to talk about the requirements that happened with these. So I've talked a little bit about the challenges, but basically we need to geolocate the beacon with high enough accuracy that it meets current standards. We need to have 3-axis attitude control to do this and to talk to our ground station, as well as generate energy. We also need to be energy positive in search and experiment mode so that we can stay in that mode for as long as possible. And then communications, we have to have enough time to downlink the data, and obviously our mass. So we used a tool called SAT Select for this. This is a GUI that's built into Warp Twin, a representative connection between the blocks that are the models and apps that you would use. And the tool called SAT Select uses data from NASA state-of-the-art to give you a pre-configured list of components, probably from some of the companies that are here presenting. And you can select those. It pre-fills in all of the parameters from that component. Then you can go run your analysis, see what the results are. And if it doesn't work, you go swap out to a different component, and you can do rapid iteration on converging to a design. So I have some examples of technical budgets that we have, that we went through with Dexter. And what's really nice is that a lot of these came from the same simulation. So you can run one simulation and it outputs all of these budgets in a nice, friendly PDF format. So you don't have to go copy paste figures and put them into reports, which our team really likes because it allows them to make these changes really quickly and then turn in technical documentation to the Air Force without having to spend hours on that. So here's an example of, here's was our first iteration of our power budget. We're showing depth of discharge in the y-axis, and so we're running a Monte Carlo run, so where the nominal case is the blue, and the gray runs are different Monte Carlo runs. And you can see that our gray lines get up to unacceptable amounts of depth of discharge. After doing some trade studies, using the SAT Select tool, collecting different parameters, we were able to get our Monte Carlo runs all to pass, as well as our nominal run, and this allows us to stay in that experiment mode and look for beacons for the entire time. I'm showing some stuff about the link budget. This is our dB link margin over multiple passes. We could talk about this more in detail afterwards, but I just wanted to show some of our analysis that we had. So we data budget, GNC, we have our geolocation performance of our actual payload, and we were able to do this all in one unified framework. All our budgets close simultaneously, which is the key part for that disconnect that we had with M-cubed. The simulation can now serve as the single source of truth for the mission. Everybody can go reference that simulation if they have questions. And then we have rapid evaluations of these design changes. So right now, we're in the implementation phase of Dexter. So we don't have our flight hardware. It's long lead times, as you guys all know. So we're doing some tech demo missions, little things that we can do in the lab until then. So we've completely built out our software, and we're running it on representative processors. So if you've ever heard of a Nucleo, that whiteboard is a Nucleo that's running our STM32 processor on it, and we can flash our flight code to it, test out our flight executable, and do some cool stuff with that. We also flew a high-altitude balloon called Navster. You can see on the bottom is our GPS track. Our top right is the picture from about 100,000 feet, and then the top left is a picture of the box when we recovered it in a field. And this was a really great learning experience for our students to test out all of our final flight operations and get an experience with this before we get our actual executable and flight hardware. So Conclusion, this is a big change for our team. This is an integrated multidisciplinary analysis and optimization. This has greatly accelerated our development and allowed us to have a lot more confidence in our process. We don't have any of those disconnected models, and hopefully this means a higher chance of success for future S&T space missions. Thank you. Any questions? Yep. So with InCubed, we accepted an orbit on a rideshare mission that we shouldn't have. Our satellite was communicating with a constellation using a radio that you can buy from commercial companies. And the way that our mission lined up, it's only a 3-day mission. We didn't have solar panels, so once our batteries were dead, the mission was over. When we launched our mission, we had a 7-day timer, and we got deployed into a polar orbit where the satellites that we were trying to talk to were in the exact opposite, so 180 degrees RAN shifted. So we were getting Doppler shifts that pushed our communications out of the bandwidth of our antenna, so we weren't making links. And so the other people who had this problem turned off their satellite, let it sit, let the RAN drift, and were able to do nominal operations. Us, we had a 3-day mission, and we were never able to talk to it. And so that disconnect, we never made the link budget and the GNC on the same on the same simulation, and so we never caught that. Any other questions? All right. Thank you.
Awesome. Thank you, Alexander. Our final speaker for session 2 is going to be Clara Davis from Cal Poly San Luis Obispo, and she will be discussing software supply chain vulnerabilities in satellites. Excuse me.
Awesome. Hello, everyone. My name is Clara Davis. I'm a master's student here at Cal Poly. I'm here to talk about software supply chain vulnerabilities in satellites. So to start off, we need to establish what is a software supply chain. In your software ecosystem, hardly anything is created from scratch. A lot of it depends on libraries. You wouldn't want to have to completely rewrite a whole operating system, right? Or unless that's part of your project. But that would, of course, still depend on outside libraries on some level. The importance here is that software needs to be verified similarly to how you would verify your hardware supply chain by auditing where it comes from. Are there any code vulnerabilities? Is this person or maintainer, especially for open source, is it trustworthy? If it's closed source, is it from a noteworthy company? Do they have a record of good security practices? Stuff like that. Every single package you import is a link in the software supply chain that you implicitly put your trust in. So you are trusting them to not hack your project downstream. You're trusting that they are not potentially including vulnerabilities on purpose, and you trust them that it works the way that they advertise that their library works. So for satellites, the issue is that a lot of them run on C and C++, and C and C++ does not necessarily have a package registry or package manager, or at least one that's all centralized. They exist for certain languages, especially like JavaScript, NPM, Python, and those will help you in creating a SBOM, which is a software bill of materials, essentially just a list of what repositories and tools that you rely on to get your project done. So to motivate the importance of software supply chain security, I'd like to go through a few examples. In 2020, the SolarWinds attack, bad actors got into their build pipeline for the Orion IT software, and the customers of that software included huge, like 10,000 different businesses, including government agencies, and it essentially gave those attackers full access to all their IT monitoring, and that would let them pivot into the actual like IT systems and into data that they might not want being exposed. In 2021, Log4j, it's a logging library for Java. That one is super ubiquitous, and a lot of people did not know that was a dependency on theirs. It's a transient dependency, meaning a developer imports a library, but that library that they import has its own dependencies which get installed, and then those dependencies get installed, and then it just kind of recurses in on itself, becomes a big, messy graph, as you'll see. And more recently, XZUtils was a backdoor targeting the XZ compression utility libraries in Linux. That was a social engineering attack by a actor that took several years to socially engineer the open source maintainer into essentially handing over the keys to that repository to them, which they then inserted a backdoor into that repository and essentially gave them control of pretty much every machine that has that utility library, and that's pretty bad. And more recently, this was just in March, the Axios, it's a JavaScript package, a dependency of a dependency pulled in a malicious dependency that allowed remote access to any system that had that package. So it's very recent and also very active in the NPM space, but I'm wanting to pivot towards C and C++ for the purpose of auditing satellites. So C and C++ projects, again, they pull all these transient dependencies. You don't know necessarily what's running on your computer. It's the dependency of the dependencies. Think like operating system libraries, or maybe already on your machine that you don't consciously or consciously like install, but they're there and they're running. And again, there's no universal package manager for C and C++ projects. The ecosystem is fragmented across different solutions like Conan, VC package, Git submodules. People will just directly copy and paste open source code into the repositories. The build systems like CMake, packages on distro registries, and it just keeps on going on and on and on. So again, it's hard to know what library is running. It's hard to know exactly which version of a library runs or where that's coming from. So in space, there's a couple of unique security challenges that present themselves to developers. Satellites can only communicate with the ground for a certain amount of time, right? So the people on the ground have to choose between, do we want our mission data to come back to us, or do we want to push up a security update? That's just a decision that you might not want to make. So you might want to audit your security before it goes up into space. And especially for supply chain, choosing which packages to import, they need to consider the mission lifespan. So sometimes you'll maybe want to choose an older, like long-term support library as opposed to whatever's cutting edge, just because maybe your satellite will be up there for 3 or 4 years and you don't want to have to repeatedly patch again. But also the fact that it's in space and that needs, there's power constraints and radiation constraints, so that limits the amount of viable software that can go up there. And so what my thesis focused on is the intersection of supply chain security and space software, because there's research on both, but not much on the combination of the two. So what I've built, I'm building upon a project that was originally meant to scan dependencies for NPM in the JavaScript ecosystem. Mine, scanning C and C++, so I'm pulling from a paper called CC Scanner that does static code analysis, and then CNEPS is code clone analysis, so that will cover the bases of maybe a developer just copy and pasting some code in there, or operating system libraries, or maybe something that you can't go onto GitHub and audit manually. And it goes into the dependency resolver, which is a big database in MongoDB, and then it will take that dependencies that it scrapes and then scrape those and recursively make a visualization. And while it's at it, it will also do common vulnerability and exposure analysis. Those are basically just cybersecurity world talk for how we are going to outline and classify different vulnerabilities. It searches that CVE database for which libraries match which versions, so we can get an idea of what is present in that ecosystem. So here we have a graph, recursive dependency graph generated by the scanner. So you can see the core flight software there. It spins off into multiple different, like a crypto library and different drivers. And so those drivers, there's, of course, they all are dependent upon this Linux driver, and that driver is also dependent upon itself recursively. And while this looks pretty straightforward, I can assure you for the NPM ecosystem, there can be there can be thousands of libraries. And so for the results and benefits of this research, I'm still going through 30 open source space repositories. I found a couple vulnerabilities, but the analysis is TBA. I'm sorry, you have to wait until my thesis is published. But what I'm hoping to do is to identify those transient dependencies through the code clone analysis and recursive search, and reveal how, which CVEs pop up the most often, which projects are more vulnerable, and how they might be able to propagate downstream throughout the software supply chain ecosystem. And then hopefully, not just for space, but it will be somewhat generalizable to the wider C and C++ ecosystem, and the tool will be, of course, hoping to release it for anyone else to use. But the costs of scanning, so far, scanning the repositories takes a significant amount of time. That is why it is still a work in progress for even a small amount, like a 30 repository data set, is because it has to query the GitHub API, clone that, do the static analysis, do the code clone analysis, and I'm building a database for all the code clone signatures, like the function hashes, for about the top 5,000 C and C++ repositories on GitHub. So it is running in a Google Cloud VM as we speak. So tools are emerging for software supply chain analysis. They're common in other language ecosystems, but not C quite yet. And during development, you might want to think about, okay, again, stable and older libraries, long-term support, they might be a requirement for physical safety of the mission. And small CubeSat teams, they may or may not, like a lot of CubeSat teams are students. Those students might not have the cybersecurity background to fully be able to audit their project. Or they might not have the time, they might be under a time crunch, work crunch, limited hours. So there's always a cost to implementing security. But in the long term, in the short term, there's a cost, it's inconvenient. In the long term, you don't want your mission to get hacked while it's up in space, possibly taken over by bad actors, and oh, the worst they can do is just cut us off from data. No, the worst they can do is just be able to command your satellite in space and do whatever they want with it. They don't just cut you off. They could actually just take the project that you probably put thousands of dollars into and make it theirs. So what you can do, just to start, create a basic software bill of materials if you haven't already. Sift is a great tool. You can point a Docker container at it, and it will, you can point it at a Docker container, and it will give you a list of all the repositories and libraries and components running in that container. Bonus points if you use Gripe for security vulnerability scanning. Sift will only show, I believe, just the repositories that you directly depend on. They don't show those hidden dependencies of dependencies, so that's where my thesis is set. Oh my gosh, sorry. That's where my thesis is unique. And CMake also has a graph visualization option. So if you want something similar to that graph that I showed earlier, again, only with the direct dependencies, that's also an option. And ideally, on your team, you'd want to foster a new cybersecurity culture. CISA has a lot of guidance on secure by design philosophies and software bill of materials and more relating to that. And please involve cybersecurity as a core component of your project design. You don't want to get hacked and lose all of your work and have it be for nothing. So in conclusion, a lot of these fragmented ecosystems in C and C++ make it difficult to audit. That is being worked on. And as the popularity of space technology and CubeSats grow, a security understanding needs to grow alongside of it, because as it continues to grow, so do bad actors interested in your data or control. They want to have access to, missions in space to potentially maybe, they'll steal your data, but they could spy on other places, they could fly anywhere else. And also the cost of building in security from the start is far less than it is to patch a satellite in orbit or having to deal with the fallout and remediation phase of a compromise. So that's all I have today. If you have any questions, please feel free to reach out to me at that email, and I can answer some right now if you'd like. I'm not actually on the PolySat team here at Cal Poly. I'm sorry. It's just my thesis research. My background is more cybersecurity. Sorry. I don't think it doesn't include any sort of like formal verification. It's just. Could you elaborate on that more?
For example, somebody has the software already, uses your tool to parse it and see if there is any vulnerabilities in it.
Okay, yeah. That is definitely a use case, but I feel generally in the security community, it's better to know what you have so you can better secure it versus just assume an adversary has the same amount of tools available that you have available. It's just, that's sort of the threat modeling that the community sort of depends upon. Mm-hmm. There's not any AI involved in the project right now. As for the CVEs, it's just querying the existing CVE database. Its goal isn't to find brand new ones, it's just to identify existing ones so developers can better understand their threat model. In terms of like software supply chain, I think there's plenty of research on Rust. I feel like any memory safety is a good thing. I think moving to Rust is great, but for the time being, C and C++ has just been the standard for so many years. So it's better to try and look at that. At least that's my research direction. Cool. I think that's all.
Hello, all right. I can use this mic. All right, thank you very much. That ends our second session. Now we have sort of an extended break. There's a lab tour going on. If you're interested in going down to the lab tour, please meet up by the indoor registration booth. And I believe that we are back in here at, I want to say 3:30 is when session 3 starts. Reminder, there's posters on floor 2, so make sure you make your way up to look at those posters as well during the break while you talk with our exhibitors. Thank you.
Hello, please welcome our first presenter, Daniel from CubeCom.
Sorry, let me adjust this. Good afternoon, everyone. Yeah, my name is Daniel Turan, and today I'm going to be sharing some of the work I've been working on with CubeCom for the last year or so. I'm not particularly good at speaking in front of crowds, but luckily, it seems to be manageable today. So, yeah, without further ado, the project is an electronically steerable antenna for high-speed data downlink. Particularly, it's got to work for small satellites in LEO. Cool. So, just a quick rundown. So the main goal of this project is to design an electronically steerable or phased or electronically steerable antenna or phased array that can point at a ground station while the satellite is pointing elsewhere. So in order to achieve a high-speed data downlink or a high-speed link, we'll first look at what's achievable with a static and pointed phased array, or not a phased array, sorry, a static directive antenna and a high-speed transmitter. And then next we're going to be looking at an ESA designed to operate or perform similarly. Yeah. So yeah, main project goals and objectives. It's got to, the design antenna has to be able to direct signal to the ground station while the satellite's pointing in another direction. So how we're going to go about that is we're going to first look at what is required to actually reach fast downlink speeds, and that's going to be through a case study. Then next we're going to look at how to actually go about minimizing the power consumed by the phased array. And then finally we're going to just look at, okay, you've got your ERP and you've got your, you've got your ERP, and now you actually just need enough elements to meet that requirement. Sure, this is harder than I thought it would be. Achieving a high-speed downlink. So first of all, we need enough bandwidth. So for that, we're going to be looking at X-band. You've got a lot, like just in general, 8 to 8.4. There's a lot more bandwidth than you get at S-band. Next, we're going to look at typical ground station performance before looking at the link budget for our fixed or static antenna and phase and transmitter. Finally, I'm just going to introduce the ESA or phased array as a concept, and then we're going to quickly talk about some of the things on it. So X-band in LEO, you'll see it's quite a lot of loss. Okay, cool, we can see it. But compared to S-band, there's about 10 dBs more loss. It's got a lot less loss than at Ka band, especially because there's no atmospheric attenuation or atmospheric effects. So this is kind of a Goldilocks zone we're going to stay in. The size of the antenna also, it's quite nice because even though, yes, we need more gain to bridge or to compensate for the larger path loss, we can actually get away with using a smaller antenna. And then finally, there are a lot of components that are actually available for or at X-band that are space grade. So, okay, cool. So the ground station is really, it's probably, well, it is one of the most important components in any downlink. In particular, what we want is high gain, a low noise floor, and a large visibility window. So we're going to look at CubeSat, and some of our clients have used them in the past, and so I'm going to use it for this case study. There, the antenna has 47 dBs of gain. That's including the LNAs, and then for a 400 megahertz bandwidth at 8 to 8.4 gigahertz, the noise floor is sitting at around about minus 100 dBm. Finally, our transmission window is from 5 degrees above horizon to on either sides. It translates to about 8-minute visibility period at LEO. And then finally on the satellite, the ground station sitting at about 67 degrees from nadir. Cool, so now we've got our transmitter, which is transmitting at 2 watts, only drawing 14.5 watts of power. And then we've got our antenna, 13 dBs of gain, giving us a total radiated power of 46 dBm. Next, we've got our path loss, which is 178 dBs of loss. And then we're going to go with a link margin of 3 dBs. If you Google it, it'll give you, it'll say maybe use 1 or 2 dBs. This is not enough. That's a bent cable is going to take your margin and just destroy it. So yeah, we prefer to be more conservative. Then, so we've got our receiver with 47 dBs of gain. And this gives us a received signal strength of 85 dBm. Which is 15 dBs above the noise floor, or 12, giving us a 12 dB SNR if we take into account that 3 dB margin. So yeah, what I really wanted to show here is that yes, we can get 9.9 gigabytes of data down by just, this is now for a 550 kilometer orbit with a single mod code, with a single coding and modulation scheme. But by stepping that and changing it throughout your orbit as you get closer or further from a ground station, you can see we can actually push that all the way up to 14.4 gigabytes of data throughput in the pass. So this is basically, this comes at no additional power cost. It's basically just hardware complexity. Cool. So now we've looked at the static antenna and we kind of have a baseline. Or something to reference it to. So the real benefit with these is you have lots of elements working together. You can see the little squares there, and by changing the phase excitation or across the aperture, you can actually steer the direction in which your main beam is pointing. So there is a trade-off to be made here, as you want there to be more antenna elements because they all radiate at a certain power, and then you need less directive gain. But each one of these has its own phase shifter and its own amplifier, so that generates heat and consumes power. But yeah, and the other thing is that these actually, or using an electronically steered phased array or an electronically steered antenna, you can very quickly change the phase delay at each element, so your switching speeds are quite rapid. This technology is really common on larger satellites, but the biggest thing is there you're less concerned about power consumption and power dissipation. And you know that kind of sucks because it's for small satellites, those are probably two of your main concerns. So first of all, we're going to just quickly look at the hurdles, like what are the key things that are stopping this technology from being readily available for small satellites. Then after that, basically, I just wanted to make sure everyone is on the same page with the key system trade-offs and why there's actually quite a big trade-off to be made with regards to your size and the amount of elements that you have. Finally, I'm going to talk really briefly about the aperture design itself. The whole slideshow was originally about designing the antenna, and then I got a lot of feedback, and the feedback was no one really cares about the antenna, which is really sad because it's the most interesting part of the system. But after that, just going to quickly talk about some of the other things or some other technologies that are advancing phased array design in general. So, okay. Yeah, there's a lot going on here. This graph shows the relationship between the effective radiated power or the total radiated power by the entire antenna array and as a function of the element power and the number of elements within the actual antenna aperture. So you'll also see there's a change in color there, and that's to show the total amount of heat dissipated as a result of all the phase shifters and biasing power. So what's really important to see here is that there's a white line, and that white line is the reference for that 46 dBm that we got with the previous transmitter and antenna pair. So anything below that isn't going to be able to make the same speed, really. So this is very oversimplified, very generic, and it's very conservative. I'm completely ignoring all the pattern gain that we're going to get from the actual element itself. And pretty much if there's at any point a place where I can say, okay, I'm not getting that much gain, I say it. And the reason for that is this is completely irrelevant of the actual antenna, or separate from the antenna design itself. So big thing, the array size is actually governed by the spacing of the elements. You need to, I've chosen to go with an oversampled aperture, and yeah, all my materials should be suitable for LEO. And finally, yeah, so I'll skip to the next stage. Okay, maybe I just want to show on the thing, on the picture, you can see there on the left side, you can see there's less power being dissipated and you're closer to the white line, so that's kind of where we want to stay. The reason for this is the effective radiated power actually grows logarithmically with the amount of elements inside the aperture, and linearly with the amount of power radiated by the elements. So you actually want to use less elements, which is counterintuitive. This shows that more clearly. So the radiated power is shown on the left axis, the power is constrained. Each of those curves meets the 46 dBm ERP spec, and then everything on the red side is not feasible. Those use amplifiers which operate at over 20 dBm of power, and they either don't exist or they are very expensive. So the key thing to see here is that for smaller arrays with a smaller number of elements, the efficiency of the amplifier has the largest impact, whereas for larger arrays, the actual biasing current of the phase shifters and the amplifiers has a larger impact. Yeah, so for the actual aperture itself, I've broken it down to like the key design elements here, and that is that my element spacing is kept a lot smaller than half a wavelength, and my elements are actually operating below resonance, and they are capacitively coupled. Then I'm using a meta-surface matching layer. The reason being it's lower profile than if I were to go with a dielectric slab, and the performance is much better than if I were to go with a similar frequency selective surface operating closer to resonance. And then this also has the added benefit of allowing me to use a high dielectric constant material for my actual antenna, while eliminating blind spots and matching it to free space. And then finally, I'm using all the outer elements are reactively loaded rather than terminated. It just allows me to transmit with more gain, or achieve a higher gain at scanned angles. Cool. And then, yeah, some of the big things that made this possible is actually using metamaterial layer, like matching surfaces. So, yeah, there's a lot to be said about them, but due to faster computation times, it's almost arbitrary to design your antenna with them. And then as amplifier technology becomes or advances, we're getting a lot more options for reducing the amount of power. Some of the big things are, GaN isn't exactly the best path for this. The reason being that if we have less elements and for larger arrays, the actual bias power matters. GaN has at this stage quite a high bias voltage that you need, and you can't really get around that because of the silicon. So GAA or gallium arsenide semi-or amplifiers are actually a better option in this case. And yeah, something else that can be done there, digital or analog predistortion could allow us to operate our amplifiers closer to saturation point, which would make them more efficient and decrease the amount of heat dissipated by the actual aperture. And then finally, stuff like liquid crystal phase shifters that are really promising. Very low bias power. It's just basically just what you need to change the actual dielectric constant of the liquid, and then you can, yeah. So it's just a very efficient way of shifting your phase. Yeah. So finally, what have we've actually gotten right, and that is we've got an antenna that is capable of steering to 60 degrees, and the 3 dB beamwidth still goes to 67. And we also have the aperture is very low profile due to the use of a meta-surface matching layer, and also it doesn't use more than 20 watts of power, which is quite a lot already, but that's quite low for a phase array of this ERP actually, and the size. And that was done by using very low or very high efficiency gallium arsenide amplifiers. And then finally, by optimizing the number of array elements and the power that and their driven power, we can achieve a design that is actually suitable for small satellites in LEO. Cool. Yeah, this wasn't great. I would highly encourage any questions. I'm a lot better at talking about things unscripted. Thank you. Hi there, yes? Sorry, say that again? Sorry, is your question, is there a reason we're not considering doing steerable antennas for S-band? I think at S-band, the free space path loss is 10 dBs lower, but I almost want to say if you're looking at, I would say really you don't need that high directionality. I take it in the amount of power you're trying to get down, or the data you're trying to get down, you might be able to get away with just a normal antenna, otherwise an omnidirectional antenna, but it is possible. It'll just be very large for a small satellite. Yeah, I think that's the biggest thing. Sorry. Yes. Oh, nice. Yes. So the key challenge here really was just getting it to work on a small satellite. I think if you made it a lot larger, I'd probably go with either just expanding the actual PCB, making it larger, having more elements there, but you could maybe, or it would actually probably be useful to create a tiled way of doing it. Or, sorry, could you repeat the question? Yes. I would probably be looking at rather just using passive phase shifters. So at the moment I'm using IQ to get my phase. It's mixing the in-phase and quadrature channels to actually achieve that. So I'd definitely go with passive phase shifters, and I'd probably avoid using amplifiers. Just in order, because it's going to grow one way or another, and the less power I have to use for each of those elements, the better. Yeah. For the gain size, if we're going to go with at X-band 1 meter, that's going to be quite a lot, maybe closer to 25, 30. Sorry, I can't do the maths in my head, but the big thing here is that the gain scales logarithmically with the size. So yeah, for smaller antenna arrays, it doesn't make too much sense to make it that much larger. Yeah, this one fits. It's a 3 by 6 inch antenna. So in centimeters, it's around about sitting at 85 to 14 centimeters. Yeah. Sorry, guys. Yeah. Mm-hmm. Yeah. Cool. Thank you. Thanks, everyone. I think, yeah. If there are no further questions, yeah, thanks.
Hello, and please welcome and help me join Jerias Abedrabo from the University of Florida.
Hello, everyone. My name is Jerias Abedrabo. I'm a PhD student at the Precision Space Systems Lab, PSSL, at the University of Florida. I'm currently working on the CLIC mission with my colleague Joseph Conroy under Dr. John Conklin. Today, I'll be presenting about how you should and should not construct an optical transceiver for a CubeSat. So for this presentation, I'll be giving a quick overview of the CLIC BC mission, and then I'll be going into some of the issues we faced while developing our transceiver. And yeah. So a quick overview, CLIC BC is a pair of 3U CubeSats. Each has a 1.5U payload that has been in development in collaboration between NASA Ames Research Center, Crosstrack Engineering, MIT Star Lab, and PSSL at the University of Florida. It has a 1537 nanometer transmit and 1563 nanometer receive full duplex laser link. We have a 976 nanometer beacon for coarse pointing between the two satellites, and these were developed using common off-the-shelf parts. So these satellites will be in low Earth circular orbit between 400 and 600 kilometers, and the goal is to demonstrate a higher than 20 megabits per second communication link alongside a ranging capacity of an accuracy of about 50 centimeters. So a quick overview of the concept of operations. Initially, we'll be deploying from the ISS through Voyager, previously NanoRacks. Then we'll do some initial maneuvers using GPS positioning. We will then do coarse pointing using the beacon laser, and then utilize the communication lasers to do cross-link and ranging tests between the two satellites in orbit. We will then try to do some commands and telemetry through RF communication to test the command data and handling system. And after that, we downlink all the tests using the communication lasers to an optical ground station. And that'll be it for the life of the mission. Here we can see some of the elements of the optical transceiver. On the top, you can see the transmitter part. On the bottom, you can see the receiver. In the middle, we have a CPU board and FPGA board. The FPGA contains all the logic, the hardware logic that contains the modulation, encoding, decoding, and all necessary elements for the control of the satellites. It has all the encoding, decoding for the transmitter and the receiver parts. The CPU board does have a Python software library to control the FPGA board. On top, you can see that for the transmitter, we have a C laser that we send through an amplifier, an ETFA amplifier, that passes through a shutter. The shutter will specifically be used for modulating a signal. And then we have a lens assemblies that will be used for transmitting the beam. Similarly, on the bottom side, you can see that we have a collimation assembly that focuses the beam initially for beam centering and pointing through a quad cell, and then it will focus the communication beam to an avalanche photodiode sensor. Here we can see an optical assembly of the optical bench. On the bottom, you can see a camera. The camera will be used to receive the beacon laser for coarse pointing. Then we do have in the middle the beacon laser that is transmitted from this satellite to the other satellite so that it can also do pointing itself. On the top, we have a telescope, and there are three different lasers, two coming in and one going out. The green one is the beacon laser that will be reflected and focused on a quad cell. You can see probably a quad cell in the middle. That would be for fine pointing. We do have the yellow laser that will be reflected towards the avalanche photodiode. That will be for receiving the data. And then we have a transmitter that sends that red laser throughout the telescope to the other telescope on the other CubeSat. So in our system, we utilize pulse position modulation, PPM for short. So to give a quick overview of how PPM works, basically we divide time into slots of equal width with a guard time slot. and each slot should be representing a value that we intend to send in time. So when we send a pulse, we make sure to have that mean of the pulse falling on top within the borders of that slot. So here you can see slot number 8 is basically the value intended to be sent. The pulse will be sent through the laser link. And on the receiver side, you can see that we have 2 thresholds. These are 2 voltage thresholds where when the signal is received, it will pass them on the rising and falling edge, recording 4 points in time. That'll be used for finding the mean of the timestamp, and then wherever that mean falls will be the value intended to be decoded. You can see that the number of values is dependent on the ppm order. So for ppm 16 here, we have 16 values from 0 to 15, and then a guard time. Naturally, this means that both the transmitter and the receiver should be in sync together. Here we have a quick architecture of the system. So on the left, we have that SerDes transmitter module, serializer, deserializer module. That will be having the encoding scheme for the ppm. It will encode and then make sure to route pulses through the hardware and send it over through an electrical or optical link. For, in space, we'll be using an optical link because we're demonstrating a laser link. But for testing, we utilize an electrical loopback link as well. You can see in the middle, we have 2 modules, TDC and ADC. The ADC module is outside this scope of the scope of this presentation. It's being developed by our colleagues at Crosstrack Engineering. However, the TDC is our responsibility at the University of Florida. It stands for time to digital converter. And then we have the data handler, which has 2 modules. One is the round robin, which will orchestrate the activity of the data channels that have data to pass. And then we have the Kelpie module, which is named after the Kelpie herding dog, which will be herding the data through the Axibus down towards the DDR. So here we only have 2 layers in our system, a command data and handling layer in Python that will be utilizing the SPI interface to communicate with the FPGA fabric. The FPGA fabric has a microcontroller that will be orchestrating any operations through control registers in the DDR. Now, of course, things can go wrong. The first thing that we've seen, or the first issue we've seen, is clock drift. As I mentioned, we naturally want both the transmitter and receiver to be in sync together. So we do that initially by doing a preamble sequence where we achieve lock, and then both satellites assume that they are on the same clock, basically. However, over time, and assuming a constant drift factor due to different reasons, we will see that both clocks start to drift, and then we are demodulating wrong values. To fix that, we have a fixed gain that we use to correct the residual. If you look at the figure, the residual is basically the difference between the mean of the pulse that is received and the center of the bin. Here we can see the difference in bin 2. And if that increases over time, we will start demodulating other values, so it will be wrong. In order to kind of adapt, because the fixed gain sometimes does not work with different orders, we're wanting to implement a Kalman filter if we take the residual to be our measurement, in addition to some jitter noise by the clock, from the clock on board, and then we assume the process to include a constant drift time, so a linear model of a constant drift multiplied by the difference in time. Then we can try to have a dynamic Kalman filter gain that will be updating on every iteration, and so it will be able to handle the changes and in the way that the clock drifts much better than actually just fixing it to a certain ppm order and then trying to just use it as is. Some other issues are during computation, because we're using VHDL and we're doing hardware through FPGA fabric. We want to do ppm modulation, and doing multiplication and division operations for encoding and decoding a ppm is really expensive sometimes on the hardware. We also don't use floating point arithmetic, and so that causes problems. If you look here, I have an example where we have a bin time that we calculate based on the formula on the right. You can see the formula says that it should be 102.4, but we assign the bin time a value of 102. And if we do the calculation using a value of 102.4 for the bottom formula, where we multiply the bin time by 10 nanosecond and then multiply by 2 for the total length of the slot width, you will get 2048. However, using a value of 102 will give you a value of 2040. These convert the regular time to TDC units, and basically here you can see that we are missing 8 TDC units, so it's a problem. The solution is to use lookup tables, like here for the residual. We have lookup tables where you can just pre-compute and map the value. So if anyone has a better solution, please help us. We also have an APD that uses high voltage. So this is not an issue we've seen. This is something to let other people know about. If you have high voltage rails, there's a lot of interference, and also using connectors can cause arcing. It happened before, and it could be dangerous to people working with it, causes permanent damage to the board. So initially we followed the standards mentioned below, the IPC and UL standards, but they mentioned to use clear markings and to make sure that the traces are adequately sized and spaced, and geometry and materials are adequate to not concentrate electric fields. This is an example from that standard where you can see on the left the voltage values, and for each cell on the right, this is the minimum spacing for the type of board that you might be using. This is the area where the most of the issues we were seeing were happening. When we were working, we're using abstracted logic, so it's functional. It's called RTL design, register transfer level design, but this is eventually synthesized to gate level implementation. So the flip-flop here becomes actual gates, which introduce delays. This caused us issues because we did not really know that this could be happening when we first started utilizing the FPGA software. Another issue that was that the synthesizer was omitting some of the design elements. So on the bottom right, we do have a double flopping solution for crossing clock domains between two different clocks of different speeds on the board, and the synthesizer just omits the second one because it thinks it's not necessary. And yeah, basically we have to specify the synthesizer attributes, so make sure to do that. Also here, you can see we also had X propagation issues. So if you had like a 0 clock, you wouldn't be able to see any X value propagate through the system. An X value is an undefined value in a signal and the simulations that we do. However, when you update it and you get a value of 1, the signal will propagate, and eventually that will happen sometimes very late in the design, and we wouldn't be really seeing it, but and it makes it very hard to go back and trace where it happens, so it's a bit problematic. So just make sure to, usually the root cause is uninitialized signals, so please make sure to, if you're working on an optical transceiver, to really trace that back, especially if you're using FPGAs. So in summary, we saw like 3 problems and the one thing we braced for. So we saw clock drifts happening, causing problems. Usually it happened in an area where we might have some laser communications because, of the time that the laser flights between both sides, and like the clock drifts and the routing issues on board because of the clocks and where they connect. And then we had problems with computation and the place and route through the synthesizer and the different elements of the FPGA design suite. And we also had braced ourselves for high voltage issues for the avalanche filter diode. So thank you very much, and please feel free to ask us any questions and give us any suggestions. Thank you. You have a question, please? So your question is, how did we utilize the SOA, the shutter, to modulate the signals? Oh, okay. So we had two parts to this. So we had an initial board, electrical board that does take signals from the FPGA pins. So we wrote the logic to do the control through the FPGA, but then we passed it to some form of op-amp and other electrical components assembly that will route to the inputs of the SOA. And then once you send the signal, it will open or close. And basically, we do have control. We just give it the binary value, will open and close, and that's how you get a pulse. Oh, okay. So the element, I'm not sure of the internals of the element because this has been procured like as a part that we bought from another company. But it's have its own internal interfacing. So, yeah. Mm-hmm. Any other questions? Suggestions, maybe? Okay. Thank you guys very much.
Thank you very much. Now introducing our next speaker, Jose Velasco from Chosky.
Thank you. Good afternoon. My name is Jose Velasco. I am with Chosky Inc. We are located in Pasadena, California. And this afternoon, I'm going to be talking about the development status of the Inter-Spacecraft Optical Communicator. We call this device the ISAC. So just as a background, the ISAC was developed initially at NASA's Jet Propulsion Laboratory, where I worked a few years ago. And then I left JPL and founded Chosky, where we are developing this technology now. So this technology has been developed over the past few years, specifically over the past 2 years under an SBIR project. I don't know if you're familiar with that. It's a Small Business Innovation Research Program, and this project is funded by NASA. Let's see. So that is the contract and the NASA. Now, the outline of the presentation, I'll include a description of the ISAC. I'll talk about the status, the development status of this terminal, and then I'll finalize with a couple of conclusions. So you can see the ISAC right in the middle. It is an omnidirectional optical terminal, has a spherical shape, as you can see there. So the goal is to place, not only develop the ISAC, but to place them in multiple assets and to create a network with those assets. So you can see here the ISAC being installed in a few small sats. And then you can see the small sats could interconnect via laser. It's in that fashion. So that's what we want to enable. And that is, we're not only developing the terminal, but we're also going to develop the network. So anybody in space could have their own ISAC and then connect to our network, and we can bring the data down to the ground. So the goals of the development of the ISAC, really three main goals. We want to do gigabit per second connectivity, multi-gigabit per second connectivity. We want to provide full sky coverage. So you don't need to steer the ISAC. The ISAC by itself will find the pairing asset and you connect to it. And in addition, we want to establish multiple links simultaneously. So those are big goals, and we are pursuing them. So this is the ISAC as a month ago. You can see It has a array of detectors, and the upper, see if I can see. Oops. Let's see if I can get. So you can see on the upper part, you can see the bandpass filter assemblies. There are 20 of those big eyes, let's call it. So we call that the angle of arrival system. So those 20 detectors, what we do is when a beam arrives to the ISAC, all these 20 elements are illuminated. And so we read the 20 elements simultaneously. And we can calculate what we call the angle of arrival. And that's the azimuth and elevation of the incoming beam. So we know where the incoming beam is. And then we have 6 transceivers. We select one of the appropriate transceivers to send a beam back to close the link. So that's how it operates. And now just to give an idea how fast it is. So if you have an FPGA running 100 megahertz clock cycle, it would take you about 10 clock cycles, literally 100 nanoseconds, so it's sub-microsecond time to detect these 2 angles. So basically what you can do is you can have tracking of the other asset at very fast rates, meaning sub-millisecond. So let's call it every millisecond, you can get a new angle of arrival. It could be even faster than that. So that's very powerful, and we tested that already. So in addition, as I said, we have 6 transceivers, and each transceiver has, you can see on the upper right, fast stereo mirrors. So there are 6 stereo mirrors. So each mirror has about 0.7 pi stereo radian coverage. With 6 of them, we can cover the 4 pi stereo radian sky. So you can see another picture of the ISAC, the goals I discussed earlier. And then some of the parameters we're pursuing right now, the specifications. We are focusing on 1550 nanometers wavelength, optical power, 1 watt. So each aperture produces 1 watt of power. And then the aperture itself is the mirror. I indicated it's a stereo mirror. And that aperture is 15 millimeters, 1.5 centimeters. And you have to give an idea of this specific ISAC, which is a development system that we're developing. Could be made a little smaller, but for now, that's about 8 inches in diameter. It's like a soccer ball, basically, to give an idea of the size. So that would still fit in a 12U or 16U CubeSat. And as I indicated before, you could, depending on the location of the other assets, you could have at least 6 simultaneous links provided by the ISAC. So we've done link budgets. I sent that last year, or before last year, I think. So here you can see, here I'm showing a plot of a link budget. The vertical is the link margin. The horizontal is distance. You see a gray area there. So you want to be above that gray area. So let's say this is for 1 gigabit per second. So in this case, if you look at a range of around 2,400 kilometers, you have a positive link margin. So you could communicate at 1 gigabit per second. And you can see the parameters we use for this simulation are on the top. So it's at 1.5 microns, or 1550 nanometers. Transmit power, 1 watt. And then the transmit and receive apertures are 1.5 centimeters. So they're rather small. And you can still get gigabit per second at 2,300 kilometers. So we want to demonstrate that. And this is all simulations. And we want to demonstrate that in the coming months. Now, if you look at other data rates, for instance, if you focus at 10 gigabits per second, which is the lower trace, the green one, you could, about 1,200 kilometers, you could still achieve 10 gigabits per second between 2 ISACs. So that, more or less, that gives you an idea of the capabilities of this terminal. And all this analysis is a paper. If you want to look at that paper, you have a detailed analysis of the link budget. Moving on, we also have developed a new terminal That's really an outgrowth of the ISAC, and we call that the compact ISAC, or the CSAC, or SISAC. So you can see there, just to give you an idea, this is 4 inches by 4 inches by 6 inches. So this is ideal for CubeSats. And this is not omnidirectional, so it can detect incoming beams from any direction, but it can only cover 0.7 pi stereo radians, basically plus minus 45 degrees in angle. So you could still have this in a CubeSat, like the way shown here, and then you might not need to steer the CubeSat. So this CubeSat will be native pointing, and then it has plus minus 50 degrees in order to find your ground station. So anyway, we are also developing that, and we plan to make this available to the community, commercially available, so that it could be installed in small satellites like this. Okay, moving on, testing. We've done a lot of testing. We have a laboratory at Caltech, being a spin-off of JPL. We have access to laboratories at Caltech, so we have 2 laboratories there. So we did all this testing, the indoor and outdoor testing around Caltech, inside Caltech and outside. And so what we did is we put the 2 terminals, the CSAC and the ISAC, on these mobile platforms. So obviously we want to move them around, change the distance between them, the alignment, and then do one key thing we did is testing the pointing, acquisition, and tracking, PAT, which is a key novelty of the ISAC. And so what we did, just for you to know, is we used the CSAC on the left to illuminate the ISAC. And you can see the ISAC is mounted on a rotary table. So we can rotate the ISAC. And we can command, say, go to 45 degrees. It goes to 45 degrees. And then we use our system to see if we can calculate that angle, how accurate that angle is. So that was that's what I'm presenting today. So you can see there's an actual picture. You can see it looks rather spacey, but it is, you see the ISAC on top, that's the main device. You see a rotary table under the ISAC, and then a tripod, a rugged tripod with multiple components to allow testing of the device. That's another close-up of the ISAC. Same with the CSAC, we mounted it on a terminal with a rotary table too for minor adjustments. And just to give you an idea, the rotary table, you can adjust it to an accuracy of a millidegree. So it's a very accurate system. And here you can see the 2 of them under testing. So again, the CSAC is on the right, illuminates the ISAC, and then what we do is we rotate the ISAC and then calculate this angle of arrival. And we check that angle versus the ideal angle that comes from the encoder of the rotary table. And you get this result. So you can see the light blue line is the ideal, and the red line is the measured. You can see in this case, it's about, for this initial testing, we can get this angle of arrival accuracy of about 0.1 millidegree RMS. So that is, again, with lights on, with fluorescent lights on, inside of Caltech. This is in the outside of our laboratories. This is outdoors. So we have now, you can see 3 p.m. in the afternoon. The CSAC is now in the picture. We illuminate it, and we do the same testing, and we get very good results. So this gives us confidence that our AOS system not only works in a laboratory setting, ideal setting, but also works outdoors with ambient sunlight present. I should mention that in this case, the noise went up, obviously. The noise in our sensors went up. But we have a way to compensate for that, to counter for that. And as long as you have the proper signal strength, you can still calculate the angle of arrival. Next, we want to fly it, and we want to put it, we are pursuing this right now. We are pursuing flight opportunities, proposals to fly this, the ISAC, And you can see on the right, we're also looking at optical terminals. For that, I've been going around all over the place, including Spain and Peru, where we are actually upgrading optical ground stations that typically are used for astronomy. We're modifying them so they can talk to the ISAC. So we already have MOUs signed with two observatories in the US, in Spain and in Peru. We are looking at also Australia and others. So the goal is to have ground stations not only to test ISAC, but also to support our network that we are implementing. So before I conclude, those are the two terminals we would like to make available to you guys. If you are interested, if you have a need for a gigabit per second connectivity or more, so those are going to come online in the coming months. And we're not only offering the terminals, but also the ground stations. So those ground stations have edge data centers. Sorry, I don't have the picture here. But anyway, so you can see there are 4 ground stations, 2 2-meter and 2 80-centimeter ground stations. They have an edge data center for data processing next to them. And it has a full-blown data center, like a kilometer apart from that, to do post-processing. So imagine a user, you can give you an account, you get your data, you can do post-processing in these edge data centers and get your data to you near real time. With that, I think I would like to conclude. We present the status of the development status of the Chasqui's ISAC. As I said, we are ready to fly it in the coming months. And also, we want to put in the market, available to the community, both the ISAC and the CSAC, so they can allow any user, could be scientific, could be commercial, could be schools, universities, to allow them to downlink the information into using our ISACs into ground stations in near real-time way, high data rates. With that, I thank you for your time, and I'm open to any questions. Yes.
So your fast-moving mirrors, are they into a closed control loop to eliminate vibration from maybe other payloads and keep the pointing?
Yes. Yeah, so they're in control loops, but as I indicated before, the key element in our system that solves or reduces that issue of vibration or jitter, any mechanical jitter, that any other component the spacecraft produce, is that our angle of arrival system allows to calculate, even imagine the ISAC moves a little bit. And our angle of arrival would calculate, it will update the beam direction in a near microsecond, and then send back the, and then transmit to the mirror. The update time of the mirror is also in the millisecond range. So imagine, so if it is anything that happens sub-millisecond, yeah, it will have some issues. But if any mechanical jitter, let's assume any movement happens in the kilohertz or sub-kilohertz, we can update and we compensate for that. Okay. Yes.
So just the ISAC, you had it kind of on top of the CubeSat. Like, how does it stow and how does it deploy? Have you thought about that?
Yes. So we have different versions, because that's a good question too. One question, we actually even developed a deployer. So it could go, depending on the operation or how you launch your satellite, it could go inside. Again, it would take that space inside your satellite, and they would deploy and stay in place. That's one. The other one is just attached to it, fixed in place, and then you launch it like that. We have other ways we can split it in two as well, depending on the application. You can have half of it on top, half of it on the bottom. For the ISAC, it's going to look like this, like one piece. We can compensate for that. So those are kind of, we looked at several configurations. But that would be. So you mean the divergence of the beam? Or the transmit beam? Yeah, so the beam is 1.5 centimeters, so the divergence is about 100 microradians. 100 microradians, that's it, the divergence of the beam. And the second question was? Okay, so there are multiple options. One is, so if you know where the beam, you have an idea where it is. So you have like ephemeris, if you know where the satellite might be, you do a search. So you have to do an initial search. So we have a paper. Yeah, yes. So we have a paper about that I can share if you want. So yeah, that's sometimes depending, because you're looking at the whole sky. So ideally, you need to know where it is, more or less, and then you do a search. There are multiple types of search, and as soon as you have a beam that goes over you, then the system will capture it, and then immediately will respond, and then you establish a link.
So what's the angular speed of the fast mirrors?
The mirrors is...
How long is that search going to take?
Yeah, so it could take hours if you don't know. I mean, anybody, if you don't have any... but the important thing is that because we have this angle of arrival system, as long as you hit it, if you get a beam on you, just one swap.
I'm asking about before you actually hit
Yes, yeah. So in that case, you need to know. So any optical terminal has the same problem in that. If you don't know what's coming, you can take hours to find the other beam because they have to find each other. There's two flashlights trying to find each other in the dark, right? So it is the same concept, yeah. So that's a real challenge. But hopefully you have an idea where they are. It might take a few minutes or even an hour to find. But like in a constellation, you will know where they are. And it might take a few seconds to find each other. But yeah, so those are kind of things. Yes. Yes, yes, yes.
Perhaps you can do something to transient temporarily broaden the
yes.
of the beam and make the raster scan easy.
Yes, exactly. So that's where we actually are looking at that, having a beam expander, adjustable beam expander. But the problem is that you're changing your power density, right? So it will shorten the range. Depending if you have enough link budget, you could do that. So expand the beam and then find it.
Maybe just for the search.
Yes, yeah. Yeah, so you can do that with an adjustable beam expander.
That's just a little more complicated.
Yes. Yeah, so we looked at that. Actually, we looked at a couple of beam expanders. And so that's something that we consider in the future. Okay. Thanks for your time.
Now, please welcome Adarsh Rajguru from Manifest Space.
Hello, good afternoon, everyone. My name is Adarsh, and I'm here from Manifest Space. And I'm here to talk about multi-purpose transponder that can be used by CubeSats as well. So the agenda for my talk today is I'm going to go over an introduction for our company and the product, address the problem that we are trying to solve, the solution that that we are pursuing, talk about our optical beacon and standard transponder and variation, which is a relay transponder for basically talking from space to space. And then we'll go over a little bit about coverage analysis, which talks about the limitations, and an upcoming flight mission with Blackwing Space, which is a CubeSat company, and then value proposition for the CubeSat community, and Q&A. So yeah, I shuffled it a little bit. I'm going to address the problem first. The growing challenge we have, not just for this community, but also for the entire industry, is space is getting extremely congested. There is a forecast of over 100,000 objects to be in space by the end of this decade, or maybe by 2032. And LEO is getting very, very congested as everyone is trying to send their constellations to LEO. And the pain point is the maneuver uncertainty and some of the collision hazards that are starting to grow exponentially are causing a nuisance to satellite operations. And it's, a single collision can be very detrimental to the entire community. So there are many solutions that exist right now for addressing space traffic coordination. There are a lot of companies out there that have different approaches to the solution. There are companies that have ground-based telescopes, ground-based radars that track objects. There are companies that are trying to put cameras in orbit to track objects. SpaceX just announced that they want to offer Stargaze as also a source of data to identify objects in space. And then there are companies, satellite operators, who themselves try to keep up with the communication of their own position and velocity as they gather it from their GPS data. However, a unique solution which has still not been adopted in this space is transponders. So in the aviation industry, we have something called the ADS-B. Even in aviation, there's for air traffic control, there's ground-based radars, but they also have transponders which work in collaboration with the existing systems. And the maritime industry has AIS, and so we looked into that as an inspiration and decided to come up with a similar product that can help with space traffic coordination and space traffic management in general. And so this is where I would introduce briefly. So Manifest Space was founded exactly a year ago, primarily to build transponders for space traffic coordination. And the product that we are developing is not just limited to CubeSats. It can be adopted by every class of spacecraft, but the lowest or the minimal version of it can be adopted into a 1U CubeSat. And transponders are currently being designed to not just serve the LEO community, but also it can be useful all the way up to cislunar, and that's something we have in our horizon as well. And we are trying to also solve the problem across all phases of flight. There are rockets and downmass capsules that have ascent through the atmosphere and descent back, which causes a lot of stress on the aviation airspace. And so the transponders are designed to not just be operational in space, but also have a handover communication link with the ADS-B network inside the atmosphere. We are considering that these devices will be useful for both military and commercial spacecraft. And the biggest pain point that I know this community always is concerned about, which is positive identification for CubeSats. Soon as it goes out of the dispenser, it takes weeks, days to know where you are, and whether you are like tracking the right satellite. And sometimes in rideshare missions, a lot of CubeSats are dispensed out at the same time, so it's very difficult to distinguish who is who. The idea here is not just become equipment tax. Usually transponders that are like ADS-B transponders in aviation were implemented because of a regulation, but we are looking at making this device an incentive more than an equipment tax. We don't know if regulations will come in and enter the space market, but the direction in which this industry is going and the congestion definitely makes sense. The regulation may come in, so we want to prepare our customers to be ready for that. We are also focusing on providing white glove service with ground infrastructure with end-to-end data pipeline. So the the information from the transponders obviously helps the space traffic management community, but there's open bandwidth for communication that the satellite operator can also utilize for many different reasons. So there are many different applications. So there are 3 variations that we are trying to bring to market in 2027. We have the first version, which is the minimalistic version, which is just an optical beacon. The idea there is it can be detected from ground, and also it can be detected by stargaze. Think of them as the strobe lights on an airplane. So you have those flashy red and green lights that the air traffic controller and even like pilots looking at you try to use that visual to stay coordinated with the traffic. So that's an analogy for this optical beacon. The standard transponder is a combination of the optical beacon and a radio that can communicate directly down to ground. And the relay transponder will be the combination of the beacon, the standard version, and also a radio that can talk to a spacecraft in GEO for relaying the information down to ground, where we can push for consistent or persistent connectivity. So let me tell a little bit about the beacon. So it is our lowest swap product. At this time, it's 10 cross 9 cross 2 centimeters. It is extremely light without batteries. If we add primary batteries, which are only used in a case of an off-nominal situation where power doesn't go into the beacon from the spacecraft, then it becomes a little bit heavier. And the idea is it's blinking, the light source blinks and transmits an ID, and also it can transmit error codes as well. We use very little power during nominal operations. We have a software-defined radio with a 9-axis IMU, so we are giving an independent source of determining your IMU data, along with the host having their own IMUs as well. We can support up to 5 optical sources. So the optical source is not tied to the electronics box. They are modular in nature, so if you wish to pick them out and stick it somewhere else on your spacecraft, that flexibility is also available. And you can have like 5 different sites, so you have the highest likelihood of being able to spot it from a ground telescope. And it is in the visible light spectrum between 500 to 700 nanometers. And we use on-off key modulation with the encryption as well. We're trying to transmit ID and error codes, as I mentioned before. That's the main goal of the optical beacon. We're not trying to do any kind of heavy communication. Some of the preliminary models that we have done shows that we can close the link by a 10-centimeter diameter optical telescope from the ground, and also be able to be visible from SpaceX Stargaze as long as the orbit is higher than Starlink. And this is the transponder version. It has a radio. It will work with your S-band antenna on board, slightly heavier due to the front-end radio components in it. And the relay version of that basically has an additional capability of communicating in KU band. So it's got quick CONOPS for the relay transponder. So the idea is the GPS signal that is received by the transponder, we can send it to the relay satellite at GEO. That data comes down to their ground station. We can directly communicate to our ground station network as well, and the beacon is being observed by our ground optical stations as well. And then we have all that data accumulated in our cloud platform, which we provide APIs for our customers to basically connect their mission control software to. A quick analysis that we did to understand, why GEO versus any other constellation, why didn't we choose a MEO constellation? It's because we realized that with MEO, the coverage was extremely poor. But having a partnership with the Geo constellation helps us get 92% of coverage. And it also gives us the window to open up the capability for 24/7 connectivity on demand. And that's something I'm sure, like, the CubeSat community would really, benefit from. And we did some analysis on the placement of GPS antennas on the CubeSat, and if that makes any issues when it comes to the internal working of the transponders. So except as if it works in all direction wherever you place the antenna, but as long as you're not putting the GPS antenna in the nadir direction, it works really well. This is something we are very excited about. We have a flight demonstration coming up where we are launching on a 1U CubeSat on SpaceX Transporter 18, and we'll be launching to a sun-synchronous orbit at 510 kilometers. We will be validating the detection of the optical beacon from ground, and we're actively working with ground-based telescopes to close that link. We're also trying to work with Stargaze. We believe our beacons can be detected by Stargaze because the orbit is higher than some of the Starlink satellites, which are in 470 to 480 kilometers, or even 450 kilometers as well. And our 1U CubeSat doesn't have an active ADCS, so we expect that there will be some tumble, which means we are kind of prepared for that by making sure that the light source is on all 5 sides of the 1U CubeSat. So the demo will be for both the optical beacon and the standard transponder. And the goal is to simulate a lost and unresponsive satellite mode as well. So basically flash an error code that says, hey, your satellite is not working, and here I am. And we can basically derive the TLE elements by using that data. And hopefully in the next workshop, we'll be able to present our findings of that mission. Just a quick value proposition for what we think will be useful for the CubeSat community. We think this can be used as an alternate radio as well. We understand that space and volume is limited. We offer bandwidths from 200 kilobits per second to 10 megabits per second. The 24/7 connectivity might be something which would be attractive from an operation standpoint of view. We definitely are making this device something that can help recover lost satellites and overall would help with reducing the burden on the space traffic management community. So we also have the option for doing some edge computing as well on board. And so overall, like if there's interest, please reach out to me. I'll be happy to answer any questions. With that, I'll take any questions. Thank you. Yes. Yep, we are having some conversations, and as far as like the flight demonstration is concerned, they're not too worried about it. But overall, they definitely feel like it's going to add more burden on operations or observations. So we understand there's some pain point there. So we just have to kind of continuously have conversations with them. We haven't found a middle ground. Sorry? That's a good question. I mean, one way of doing that is going away from the visible spectrum, but I don't know if their observations are in wavelengths which would again be incompatible with what we choose. But honestly, I don't have a good answer for that right now. Our focus is mostly on space traffic management resolution, and I don't have a really good answer for that. Yeah. Yeah, so this MVP that we are implementing in the flight project has got a battery life for 3 months. We are eventually looking to extend that for the flight, the production version of it. But at least for the MVP, it's a 3-month lifetime. Oh, sorry. No. Okay. There's a lot of glare, so I can't see if anyone is raising their hands. Okay. I guess we good? Yeah, cool. All right, thank you.
So next we have a presentation on experimental optimization for LED-based downlink from low Earth orbit. Please help me welcome Andrew White and Nicholas Tenorio from the United States Naval Academy.
Hello, everybody. My name is Midshipman Andrew White.
I'm Midshipman Nicholas Tenorio.
And this is our presentation, USNA 20 Sauron, and it is about optimizing LED-based downlink from low Earth orbit.
Yeah, so what we'll talk about today is the overall mission objective of what we're trying to do with USNA 20. We're going to talk about the spacecraft itself and its integration with the multiple 3U satellites. And then we'll go into the actual payload. We'll talk about its ADCS and its LED systems. And we'll talk about its military application.
So the purpose, radio frequency, I'm sure you all know, is very common on satellites. It's common for communication essentially everywhere. But if you've seen the Ukraine conflict recently, drones are being flown with fiber optic cables instead of radio communications. So it's very, very, it's extremely easy to jam radio communications to a point where there's been a recent study that showed that it would be easy for China to send about 1,000 drones up over Taiwan. They could essentially deploy these jammers and completely mute communications for the US and allies in that area. This would obviously be a huge issue for a lot of reasons. A little bit of what we're looking to do is hopefully create a system that the military could potentially use in a conflict like this to bring back some semblance of effective communication with troops on the ground or ships in that area. So another issue that we had to figure out was using LEDs versus lasers. We initially wanted to use lasers and realized that higher pointing accuracy, the single point of failure with a laser made it more difficult to create a really low-cost system, which is what we're looking to do. We want to be able to throw up as many satellites as we can very quickly into a situation where maybe higher orbits or pretty much every orbit is compromised and satellites are very likely to be destroyed in a large-scale conflict. So our mission objective, we want to demonstrate extremely low-cost downlink from low Earth orbit. We want to develop a standardized process, especially for ground stations. And then we want to determine like our signal-to-noise ratio. We want to figure out what atmospheric conditions do to our data rates, to our reliability, how we're able to communicate in different situations. And then also just the general feasibility of a system like this for some sort of large-scale conflict.
So when we go into the spacecraft itself, the first U is the Naval Academy Standard Bus, which has been developed over the past few years. And that integrates with the 2 payload U's, which include the LEDs, which for the optical communication, and because of the required pointing accuracy, it has an attitude and determination control system. The also thing that is included at the very top of this system is a thermal management because of the heat produced by the LEDs. The general layout, like I said before, the NASB is at the very bottom, and there's integration in the middle layers, and the very middle on the flat side has the layer with an array of multiple LEDs, and the ADCS system that we're using is currently being developed from a company called CubeSat, which we'll go into next. And the development of this ADCS system is shown by the concept operations. We'll see how after the deployment of the satellite, it'll be in a tumble state. So we'll use the multiple components of this ADCS for a detumble mode, which is followed by a deployable magnetometer, which increases the distance away from the satellite itself to protect from some of the magnetic interference. And then you go into using sensors, such as the sun and earth sensors, which are used in conjunction with the actuators, such as the cube wheel and the torquers. And this creates a stable 3-axis stability that is used for the overall idea of LED communication and consistent pointing accuracy as you travel across. Now we'll talk about the ADCS itself. Like I mentioned before, it is from CubeSpace as a Gen 1 system that was used in previous years from midshipmen. And right now we are trying to reintegrate this into our current project. And what we've been doing is taking each individual component, performing health checks on them. And here's an example of an image that we've produced. There's the example on the top and the picture that we've produced as midshipmen on the bottom to try to replicate the horizon sensing. And as we continue, we're going to integrate this into the USNA 20 project and perform continued mode testing, such as detumble. Here's a breakdown of the system that we have currently. One thing to note is the array of the sensors that we have, such as the sun and the earth sensors, are on a midshipman-created board that will continue to be developed as we integrate it into the project itself to fit around the LEDs and to fit around the thermal management systems. The other actuators that will be used, such as these cube wheels and the torquers.
Sorry. There we are.
Here we are.
There we go.
Yeah, so these actuators, these will be set up behind these LEDs and within those 2U payload in order to create that stability, like I mentioned before, that will be used for the LEDs.
So the LED payload, our payload, it consists of 36 LEDs. They'll be varied in power. We'll have a few much higher power LEDs and then a variety of lower power LEDs that will allow us to test different communication schemes, test how we're going to use the different LEDs in different communications that we might be doing and how we will adjust it for mainly atmospheric conditions and other potential interferences that we might face in, like, a cloud can be a significant issue for something like this, of course. Our high power LEDs are going to be closer to the heat sink, and we have a thermoelectric cooler along with some pretty significant cooling because we're going to look at about 20 watts of power that we're going to be creating, and we're going to hopefully be able to dissipate all of that with the cooler, transferring it away from our critical components. The LEDs are also going to be collimated, especially the high power ones are going to be collimated to about 8 degrees, which means we need significant pointing accuracy to some extent, but it's not like a laser where we would have to be much more accurate, which would make our system potentially much more expensive. So the LED configuration, we've limited ourselves to a silicon sensor, so we are going to be mainly in visible spectrum, which also happens to be an area where atmospheric transmission is pretty high, so it works out in some ways for us. These 4 wavelengths are what we've chosen, and the near IR wavelengths are the ones that we're going to be hopefully looking towards using for a system if this were to be implemented on a larger scale. You can see there how the atmospheric absorption and scattering is, like, what different things it's due to, and we're trying to sit in kind of lulls. You can also see with the red line showing the difference between a dry and a wet day is also very significant in terms of how much signal we can get down to the ground. So our procedure, first we establish radio communications from our ground station at USNA. Then the difficult part in a lot of ways is locating and tracking. We have in the past, MPS created a satellite that has a secondary payload of 9 lower power green LEDs. We've been able in the past to track their satellite from our ground station using those green LEDs. We're going to have significantly more power and, of course, more wavelengths. The idea would be hopefully we can recreate our tracking ability and also get better at it to potentially try and shift the lessons we've learned and use them for others at the Air Force Academy, at the Naval Postgraduate School, and hopefully others somewhere in the field or in the fleet to be able to recreate this more easily than we have been doing it. Recently, it's been a fairly difficult challenge, especially with the low power, to keep this in our frame and establish a strong communication link. Finally, we'll be using first-order diffraction to determine the relative intensity of all of the different wavelengths, where the 4 wavelengths can each represent 1 bit, or we can adjust our communication scheme as needed based on conditions. So the impact. Hopefully we'll determine power requirements for reliable communication at these wavelengths. Also, we would very much like to develop best practices for ground stations, as I mentioned. That is one of the big things that we think could be or that has been a challenge for us and will likely be a challenge if this is attempted to be implemented outside of our USNA and other similar ground stations. And finally is demonstrate that this is a feasible system that can do something hopefully effective and help at some point our military and to keep some bit of communication, no matter how small it may be. This would be fairly slow in terms of data transfer. If there were to be a large-scale conflict and there were to be some sort of debris field in space, I'm sure that would not be particularly fun for the attendees of this conference, but that is a concern, especially in a large-scale conflict.
Thank you all. We are open to any questions.
Nothing?
Yes.
We have a budget of about 20 watts total. We're going to have, I believe, 6 lower power green LEDs. I think they are a little under a watt, and then 3 LEDs of about a watt each. Yes. Mm-hmm. Yeah. So we have done some vacuum chamber testing. We're going to do a lot more, I know. The hope is we're not going to be continuously communicating. Of course, in a low Earth orbit, the time that we're able to see the satellite is on the scale of minutes. The hope would be we communicate, we do whatever we need to with this communication, then we let it go and cool off, give it some time, just to radiate away the heat. We will have a heat sink on the top of the satellite, but yeah, the idea would be we're not continuously putting out 20 watts of power into our satellite, as I think we would fairly quickly destroy it. Good.
Yes. At the moment, our current slot will be for about January of 2027, and we're meeting with the Department of Navy to continue to look into opportunities.
Yeah, we presented recently to a space experiment board and are waiting on the results from that, but it's going to depend on when they are able to give us a suitable orbit for our project.
Yes.
Did you hear that? Can you speak up, please? I'm sorry. Yeah, so the divergence of our higher power LEDs is going to be a little bit smaller. The low power ones are internally collimated, and it'll be around 15 degrees. The high power ones, we're looking to be about 8 degrees at full width half max. The attitude control should be within about a degree or two. It should be significantly more accurate than that. So we should be right around the center of our beam if we're trying to point at a particular ground station. Yeah, go ahead. So was it how many ground stations?
Yeah, was your question how many ground stations?
Okay, so yeah, so the number of ground stations we have currently, right now we have our ground station at USNA. The Naval Postgraduate School has one, the Air Force Academy has one, and then there is a I forget what it's called. There's a school in Georgia that we're working with who also has the capability. We are hoping to eventually extend this to make it so that it's fairly easy to set up a ground station, somehow that would be able to receive a signal from a system like this. But currently the fairly high beam divergence means that you need fairly significant tracking capabilities to be able to do that, so it isn't quite there yet.
Yes. Yes, we're testing multiple at the same time in order to provide the best for the 3-axis stability, especially when we're trying to point during the pass. And you have to take into account factors such as the power consumption, and those are such as the things that happen for the short period of time only for the ground passes. And that is why we're testing all at the same time. Thank you. That is about all the time we have. I appreciate you all listening to us. Have a great rest of your day.
Thank you so much.
All right, that concludes session 3. Thank you for everyone who is attending to the last. You didn't run off to the networking dinner yet.
Awesome.
That's our next event, networking dinner. It's over at the Hub. It starts at 6 p.m., so I hope to see you there. And then we'll start back. I misread the time last time, so let me make sure I get the time correct. We'll start again tomorrow. There's a breakfast that'll be open starting at 9, and then we'll start again with talks about 10:15 or so. So I hope to see you tonight and again tomorrow morning. Thank you very much.